Hello, thank you for joining us today. This workshop is being recorded. My name is Danielle, and I'm one of your Solid State Circuits Society staff members. We welcome you to today's Solid State Circuits Directions workshop on solid state circuits and devices in extreme radiation environments. Please use the Q&A section on your dashboard to ask any questions. The workshop video and slides will be posted on the SSCS Resource Center. You can find the link to that in the chat. I now invite the organizer of this event, Moritz Ortmans, to give a few welcoming remarks.
Thank you very much, Danielle. Thanks everyone for joining in this session today, afternoon in Europe, early morning in the US, and already late evening in Far East. I'm very happy to basically host and co-host this wonderful opportunity workshop on solid-state circuits and devices in extreme radiation environments. Let me first thank our 6 distinguished speakers. I'm going to introduce them later on when it's about to listen to their talks. Especially, I want to thank Cristiano Caligero, with whom I had the pleasure to basically organize this workshop now for almost more than a year, because I attended his wonderful pre-workshop tutorial at ESROC in 2023. Long story cut short, it is really a pleasure to have this running today. It's a topic which we are not so often basically coming in touch with, and it's a topic which basically brings together electron devices, reliability, integrated circuit engineers, and I'm pretty sure we are going to see a fantastic round of talks today. So Danielle, you're going to officially start, or are we going ahead with just the first talk from Sumjajit? Danielle?
Yep, we can begin.
Perfect. All right. So then it's my pleasure to introduce Sumjajit Mandal. Actually, he received his bachelor of technology from the Indian Institute of Technology in Kharagpur in India in 2002, and the master science and PhD degrees in electrical engineering from MIT, the USA, in 2004 and 29 respectively. He was then a research scientist with the Schlumberger Doll Research in Cambridge. He was an assistant professor at Case Western, and then he became associate professor with the Department of Electrical and Computer Engineering at the University of Florida. In 2022, so 22, he became a research staff member with the instrumentation division at Brookhaven National Laboratory. He is very distinguished in publications, almost having 200 publications in the field, more than 25 patents, and his research interest basically going to precision instrumentation for various radiation sensing and biomedical device applications. It's my pleasure to introduce Sumjajit, and if you want to start with your talk on radiation effects in semiconductor components, please go ahead.
Thank you, Moritz. Hope everybody can hear me. Let me just share my presentation. And I'll put this into full screen mode. So thanks for organizing this workshop, and it's great to get this workshop started. So I thought what I'd do with this is to give you an overview of the interaction of radiation with matter, which hopefully will form a good basis for the later talks, which will deal with specific applications and ways in which we can counteract these effects. So this will be more of a physics talk. There'll be a little electrical engineering, but it's mostly more on the physical basis of the interactions and what drives them and what drives the various damage mechanisms. And then I'll end with a few examples of typical radiation environments that we might encounter and the sort of performance requirements we might need there. So my name is, as Moritz mentioned, I'm Sumjajit Mandal. I'm at the Brookhaven National Lab as the outline of the talk. So like I said, I'll start off with an introduction of the interaction of radiation with matter, and I'll talk a bit about the types of radiation damage that result from these interactions, things like displacement damage, total ionizing dose effects, which are both cumulative effects, as you'll see, and then single event effects, which appear from a single interacting particle. Then I'll talk a bit about the impact of technology scaling, because as we know, industry is driving forward with downscaling to very, very small nanometer-sized devices. So what effect does radiation have on those? We'll see it's kind of a mixed bag. Then I'll talk, like I said, a bit about a few examples of high radiation environments, including space missions, particle accelerators, which is something that we work on at BNL, and nuclear reactors. And then I'll conclude. So a few words about BNL. So we are one of the Department of Energy's labs. We are national labs. We are supported by the DOE's Office of Science. We are a multidisciplinary lab with several Nobel-winning prize discoveries and over 70 years of research. We have about 3,000 employees. We are located about an hour east of New York City in Long Island, and we have various areas of research. But most important here probably is our strong focus on nuclear science, which has been a feature of the lab from the beginning. Recently, we've also ventured out into other areas. We also have a bunch of user facilities, among which is the synchrotron light source, which is one of the brightest X-ray light sources in the world, and is also called the NSLS2. Now, in particular, I'm part of the instrumentation department, which supports basically the mission of the lab in all these areas. In particular, we have a strong set of capabilities in radiation detection, including both everything from sensors to gas and noble liquid detectors. And what's of most interest here is I'm part of the ASIC group, so we work on a variety of application-specific ICs for radiation detection, front ends, back ends, processing. Also going down to once the data has been acquired, you need to process it. So we also have groups that work on high throughput data and triggering and data acquisition. We also have groups that do CAD, microelectronics assembly, photocathode development for detectors and accelerators, and also quantum information science. So we do a variety of work in this area. So with that, let me just jump into it. So the main focus here that I can start off with is how particles, which are energetic particles, might interact with matter. And here we must think about the fact that we have various types of particles, a wide range of particles that could interact with your circuit or electronic device. Maybe it's worthwhile going through briefly a few of the most important types and what sort of effects we see before beginning with some of the general effects of these particles. So the first one here to talk about really is photons, energetic photons, X-rays or gamma rays. You can think about interacting with an atom here shown in the middle with the nucleus and rings of electrons around it in three basic ways. One of them is the photoelectric effect, the famous photoelectric effect originally explained by Einstein. And this is where you have an interacting photon releasing a photoelectron, which is one of the inner shell electrons typically. And this becomes a photoelectron, which can then go and cause more damage. On the other hand, you can and then in the process also release an X-ray photon, which can then go and continue and cause more effects further effects to be created down the line. So this happens dominantly at low energies. You can see that if this graph here is the mass attenuation coefficient. So what ends up happening is because of these effects, the light beam, photon beam gets attenuated roughly exponentially following this Beer-Lambert law, which is probably familiar to most people. The coefficient here, which is basically normalized by the density, is called mu, the mass extinction coefficient, which is how rapidly the attenuation happens. And here we've plotted this versus energy. This data is taken from the NIST XCOM database, which is public. Now, you look at it, you see at low energies, you get this strong effect from the strong attenuation from the photoelectric effect, which is dominant. You get discontinuities in this, and these correspond to particular energies which correspond to enough energy to ionize one of the inner shell electrons, such as the KH in this case, which is the K shell or the innermost shell of a heavy atom. So this effect gradually weakens as you get to higher energies, mainly because the interaction time available decreases, and then also the match to the energy levels of atoms, which is in the tens of kiloelectron volt range, it becomes less strong. So then, as the energy increases, other effects take over. So one of them, which is actually prevalent over a broad energy range, is inelastic scattering, which is also called Compton scattering. Here you can see there's two shown, coherent and incoherent, the blue and the green curves, and those appear over a broad range of energies, but are usually not dominant, except in the kind of the middle energy range around, let's say, 100 kiloelectron volts to about a few mega electron volts. And then the third production mechanism, which becomes really important at high energies, is direct pair production. So essentially, when the photon has enough energy to generate electron hole pair, which is about 1 MeV, and above that, you can see there's a threshold. Above that, you get electron positron pair that gets generated, creating potential for a cascade. And this happens both in an electron environment and a nuclear environment, and this will take over and become the dominant mechanism at very high energies. So overall, you get this kind of complicated mass attenuation coefficient. But the key point to remember is these all add up together to give you the net attenuation coefficient. And by and large, the attenuation as a function of depth of penetration is still exponential for protons, but for photons. But we'll see this is not true for other energetic particles. The next thing we should probably consider are electrons. So if you have incoming electrons again coming into a nucleus, I mean an atom which has a nucleus and shells around it, there's again 3 or 4 major types of mechanisms to consider. The most basic one is elastic scattering, where energy is conserved. So the electron basically just gets diverted in its path. You can also have inelastic electron-electron scattering, where the electron gets diverted, and you also have recoil. So the electron that's stuck carries off some of the incoming momentum. And you might also have a characteristic X-ray photon getting generated. You have inelastic scattering between the electron and the nucleus. And this often gives you this generation radiation called Bremsstrahlung or breaking radiation, which is what happens when there's a change in momentum due to the inelasticity of the collision. So these secondary products, which are inside, which you can see are electrons which change momentum in some cases, and these Bremsstrahlung, which is broadband radiation, and also the narrowband characteristic X-ray photons from particular ionizations. These all go off and can create these secondary particles can then go off and create their own events, so we can have the potential for a cascade. Then the next thing to consider are probably nucleons. So nucleons are protons or neutrons, and they have somewhat different behavior. But to simplify, let's consider neutrons first. So neutrons, you can have 2 types of major types of events when you have a collision or a near miss between a nucleus and a neutron. So one of them would be elastic, which means energy is conserved, and the inelastic, which means there's some energy loss in the process, again, just like with the electron interactions. So with an elastic collision, what happens is the nucleus will recoil because energy is conserved, but there's a change in the momentum of the incoming neutron. So that change in momentum gets imparted to the nucleus, which moves, and this causes displacement of the nucleus. So this is you can see potential cause for displacement in the lattice. Then you might have inelastic nuclear collisions, where energy is lost, and here the nucleus ends up first being in an excited state and then undergoing a variety of nuclear reactions. So these could give you the excited state could decay, giving off a gamma ray photon. There could be fission. There could be light fragments getting generated. Fission generates 2 equal or similar size fragments, or you can have an ejected neutron or proton, which is also called spallation. So all these can then these secondary products just like in the other examples can then go off and create their own products, and you can sustain that through the material. But the types of radiation damage, then, based on what you said, you can think about ultimately as resulting from energy absorption inside the material. And the first thing that can happen is because of, for example, electron interaction with the photon or an electron. Like we said, we can have ionization. So this ionization can happen anywhere along the particle trajectory. So this creates what we call an ionization track. The charge that is generated along the track can either drift in an electric field or can diffuse, and then eventually can get trapped at neighboring interfaces. And when this trapping happens, or when during the process of this trapping, you have transient electric fields and terminal voltages getting generated, and these are called single event transients. And this is while this charge cloud is still moving. But once the charge cloud has stopped moving, you get gradual static changes in device characteristics, which are called cumulative effects. And these appear after the cloud gets trapped. So you can see that you're both going to have instantaneous effects, which are the single event effects, and these slow effects or static effects, which are cumulative and get worse with time. And so therefore, given let's look at the static effects first. So the 2 main damage mechanisms that we'll talk about are displacement damage. Remember, we said that a nucleus could move because of recoil, and so this is one mechanism for getting so-called displacement damage, where radiation will displace atoms of the semiconductor from their lattice sites, creating defects. Or there could be ionization damage, which is caused by absorption of energy, right, which we talked about. And these effects can either be reversible or permanent. In practice, actually, nothing is permanently damaged. I mean, in other words, almost all types of damage will eventually self-recover to some extent. As we'll see, this process is called annealing. And so this is a very dynamic and time-dependent process. So you might cause damage, but then the damage will gradually either increase with time, which is called anti-annealing, or to get worse with time, it's called annealing. And so these can be reversible to some degree or not at all. So wide variety of time dependence here. But then two common types of damage that are caused by this type, common types of performance changes that are caused by this type of activity are increased leakage currents, which we'll see at reverse bias PN junctions, which could be inside transistors or inside diodes, and then changes in effective doping levels. And these will drive a lot of the changes we'll see in terms of cumulative effects. Okay, so radiation units. So it's worth talking a bit about radiation units because people use a lot of units, and it's good to be clear about what we are using. So for ionization damage, unlike displacement damage, let's start with ionization damage first. It mainly depends on the total amount of absorbed energy per unit mass, which is also called the dose, and not so much on the type of radiation. And this dose is typically measured in the CGS unit called rad, or in gray, which is the SI unit. It's easy to convert because 1 gray is 100 rad. And as you can see, this is just a measure of energy deposited per mass, so joules per kg or ergs per gram. The ionization damage is proportional to this total ionizing dose, which is expressed in rad or gray, but it should be referred to a specific absorbing material to facilitate comparisons. For example, people will write 1 rad of silicon. Then the charge that's generated by this ionization, you can say, is this QG, a generated charge, that's equal to the energy per ionization energy per electron hole pair, which is called delta, and the symbol is not showing up there. It's inverse proportional to that. And this is proportional to the band gap. So you can see here there is a dependence on the semiconductor material, because materials which have a bigger band gap will have a higher ionization energy per pair, and therefore for a given amount of absorbed energy, which is E absorbed, they'll generate less charge. And then there's an additional term there, which is called EPN, which is energy loss due to phonon generation, because this will also generate, there'll be some energy loss due to vibrations of the lattice, which are called phonons, quantized vibrations of the lattice. And then much higher values are of this delta, which is not showing up the symbol, in the tens of eV range, are required to generate electron ion pairs. So these would take more energy, typically 10, 20 eV. Okay. Then in terms of modeling these particle matter interactions more precisely, the radiation dose, like I said, is defined as the absorbed energy density. But you can think about this also as a measure of the interaction between the ionizing particle and the particular material. How strong is the interaction between them? And this interaction strength depends on multiple parameters, like we said, the type of particle, the material, and of course the track length, because the longer the particle has to interact, the more interaction there will be. So this is generally quantified then by the energy loss per unit length, which is a suitable measure of interaction because it says how much energy does the particle actually lose as it travels a unit length inside the material. And this is an important quantity, and it's called the stopping power or the linear energy transfer coefficient, or any linear energy transfer metric, LET, typically expressed in units of kiloelectron volt per micron. But people will sometimes also normalize it by density, and you'll see units which have density in them. But if you don't do that, it'll just electron volts or kiloelectron volts per micron or per meter of travel. Now, the TID can be obtained by integrating the LET over the spectrum of the source, because the LET is energy dependent. So in order to account for that, you have to take the energy distribution of the source, which is its spectrum, and integrate the LET, which is DEDX, over the entire spectral range, and that gives you the TID. And then an interesting analytical expression, which only works for charged particles, but is kind of interesting, is this expression which shows that the DEDX, which is the LET, is proportional to the slowly varying function of E, which is called Fe, square of the particle charge, and inversely proportional to E by m, which is the energy per unit mass. Now, the interesting point is energy per unit mass is a measure of particle velocity squared. So you can think about classically it would be measured up, it would just be half mv squared is equal to E. So this is just b squared by 2. So this is telling you as the particle moves faster, there is just less time for interaction to happen, and therefore the LET decreases. So as the particle becomes slower, there's more time for interaction to happen, and there'll be a stronger interaction. So that's basically the message of this equation. And you can see that here, interestingly. So as we remember that photon beams attenuate exponentially, you can see that here. This is the depth. This is actually a picture that I took from Wikipedia, where it shows this is for important for people who are doing proton therapy, for example, for treating cancer. They want to know where the energy is going to be deposited inside the tissue as a function of depth. So you get typical curves like this. If you have an energetic photon beam, 6 MeV is in the gamma ray range, it still attenuates exponentially, pretty much like we'd expect. But if you look at a proton beam or an ion beam, you'll see that it has this very characteristic profile where the LET will gradually rise and then suddenly peak at this point, which is called a Bragg peak. And the reason for this is related to the equation that we saw before, because what happens is as the electron beam propagates, it loses energy. which causes it to slow down, which increases the LET because there's more interaction time. And you can see there's a positive feedback loop that's getting created. Eventually, the loop gain just blows up, and all the energy gets deposited. Most of the energy gets deposited at this particular depth where the particle has almost come to a stop, and so that's the maximum length for maximum time for interaction to happen. And that's what's called the Bragg peak. And this distribution is, if you're a radiotherapist trying to treat a tumor, you would want to tune the energy of your beam so that this absorption happens right at the depth you want, the tissue of interest. The other point to note here is that here we're looking at proton beams, but other heavy ions will have similar characteristics, but in general have much higher LETs, and therefore they're even more disruptive than a lighter particle like a proton or a neutron. And this explains actually why most single event effects are dominated by these heavy ion strikes. If you have an iron nucleus hitting you, or even worse, lead nucleus hitting you, you're going to get much higher LETs and therefore much higher energy getting deposited and charge getting created than for a lighter particle or a lighter nucleus. The last point to note here is that the effects are also dependent on the angle at which the particle hits the substrate. So, this is easy to see. The actual LED does not change, but what happens is because most semiconductor devices are fabricated with layers that are parallel to the surface of the wafer, if you hit the wafer at an angle, let's say theta to the normal, as they get further and further away from the normal, there is just longer distance of travel for the particle through the actual layer. And so you can model this by defining an effective LET, which is the actual LET divided by cosine of theta. So you can see that angle strikes are going to give you a larger effect inside your device. Okay, so to summarize, what we've covered so far is that we have these two types of basic effects: cumulative effects, which we talked about a lot, total ionizing dose and displacement damage. And then single event effects, which we haven't talked about yet, but we'll talk about. And this is caused by a single ionizing particle. And you can characterize these by various metrics such as TID in gray or rads. And then displacement damage, which is often expressed in terms of the fluence, which we'll see is the total number of particles per unit area that's incident over a given length of time. And this is often often expressed in terms of equivalent neutrons. So, and you'll often see this term NEQ. And then stochastic effects typically happen because of energetic particles, which could be hadrons or heavy ions, and these are often also expressed in terms of fluence, which is per centimeter square. And like we said, these effects can be either destructive or non-destructive. And other components in your system, apart from the electronics, things like your packaging or your magnets, if you have an accelerator, or your cryogenic components, can also be affected by radiation, or optics, for example, as well. So to summarize, we have these two major broad categories: single event effects and cumulative effects, but they do overlap. And when they overlap, we have these interesting dose rate effects, where it's not just because of a single event, and it's not a cumulative effect, but it also depends on things like how fast your particles are hitting you, and what is the rate at which these particles hit. So we'll talk a bit about these dose rate effects as well. Okay, so talk a bit more about displacement damage. The terminology here is that the energy that is required to create displacement effects is about 20 eV for silicon. And the energetic particles, which are much more energy than that, will just create clusters of defects, as we'll see. The resulting damage is not proportional to absorbed energy, but rather to this quantity called the non-ionizing energy loss, or NIEL, which depends, it's not just dependent on energy, which is why it's not proportional to energy, but it depends on other properties such as particle properties, mass, charge, energy, and the total number of incident particles per unit area, which we saw before is called the fluence. And as we saw, actual fluence is often converted to equivalent fluence of 1 MeV neutrons. So here's an interesting graph which shows the displacement damage intensity normalized to some unit as a function of energy for different particles. You can see protons get steadily weaker as energy increases. Again, this is mainly because they're just moving faster, so there's less interaction time. On the other hand, neutrons actually get stronger. Their effect is stronger as they may be as the energy increases, and that's because neutrons are not repelled, and so they're not subject to this limitation that they're repelled by the nucleus because they're not charged. And electrons have similar characteristics to neutrons, but have much less mass, and so they are much less. They get much less energy per collision than the neutrons, and so they're much less effective, about a factor of 2 orders of magnitude worse, weaker. So these characteristics are important, and these characterize displacement damage, or NIEL. Okay. So displacement damage, what does this cause? There are three main effects that happen. The first is that you can create, because of these defects, allowed states within the semiconductor band gap. And broadly speaking, you can divide these into two categories: defects that are close to the middle of the band gap, these are called mid-band gap states or mid-gap states, and those that are closer to the valence band and conduction band, these are called the trap states. And then these cause changes in the doping density of electron donors or acceptors. And I mean, sorry, in addition to that, you have changes in the doping density of electron donors or acceptors. So the mid-band states create generation and recombination processes, and this causes current flow inside, for example, reverse bias PN junctions, which is going to cause which is going to cause effects like changes in beta, your current gain for a BJT, or increased leakage current in the gate of a JFET, things like that. In the valence band, you have trapping of carriers by charge, trapping of carriers by these trap states because they're close to the valence or conduction band, and this will generally give you increased device mismatch 1 over F noise, which are well-known processes that are mediated by traps. The last point is the changes in doping density. So you can model this by sum of several terms. So here this is the effective doping density of a certain layer as a function of the fluence phi. There is an exponentially decaying term, which is the fact that donors are getting removed. There's a growing term, which is the fact that acceptors are getting generated. But then there is something that actually degrades or decreases the effect of this acceptor generation as a function of time, and this is this annealing effect I was talking about. There's an annealing time constant, and this causes the effects to gradually decay with time as the system settles back towards an equilibrium. And there's also an anti-annealing term which sometimes affects, and this is a function of temperature T. So these changes all have a complex effect on your doping profile if you have a device, and this will obviously cause changes in things like your saturation currents inside a junction, for example, and depletion region widths, which will affect things like capacitance, minority carrier lifetimes, diffusion lengths, mobility. Basically, all the various properties of the device will be affected by these changes in doping density. Okay, displacement damage. The important point is that displacement damage processes are proportional to device volume, and therefore they primarily affect bulk devices like photodiodes, solar cells, CCDs, BJTs, JFETs. Surface devices as MOSFETs have small volumes, relatively little affected. And for BJTs, the main effect is the decrease in the DC current gain at low currents because of these mid-band states. For JFETs, the main effect is an increase in the gate leakage current. And generation new acceptor sites typically has little effect on BJTs and JFETs since they both operate at relatively high doping levels, but other devices which have lower doping levels like PIN diodes, for example, might be affected. So here are some interesting graphs which show the effect of these simulated effect of vacancy distributions in silicon projected over a depth of a micron for certain fluence. You can see that low energy protons have this kind of nice uniform pattern, whereas as you get to higher energies, you get tracks getting created in clusters. And the neutrons have this very characteristic cluster-like creation of defects. So quite distinct from that of protons. Okay, so I already talked a bit of TID effects and the effects of interface and field oxide traps, and these are relatively similar to those you get from displacement damage as well. Increased reverse leakage current, increased base current, increased collector current. The one interesting point I'd like to mention here is there's an interesting enhanced low dose rate sensitivity effect, or ELDERS, which shows up, which is that when you plot the effect of these TID or displacement damage on a device, you'll find that it's often enhanced at low dose rates compared to at high dose rates. But this is really a misnomer. What we should really say is that there is a suppression of the effect at high dose rates rather than the reverse. And this happens because of various processes, typically driven by recombination. So one likely mechanism is that you have electron recombination between electrons and holes or protons in the base oxide at high dose rates, which reduces the buildup of interface traps, which is what is driving the increase in leakage current. And this means that effectively this actually is important mostly during testing, because if you're going to test a device at low dose rates, you might find that it's having a much stronger effect than you actually would have when you extrapolate that to a higher dose rate if you don't take these ELDERS effects into account. Okay, on MOSFETs, the main effects of a TID would be things like threshold voltage shifts, changes in the subthreshold slope, and mobility degradation, and you have increased leakage current, particularly for both bulk and SOI technologies, and you have increased inter-device leakage and increased static supply current. The way this happens mostly is that you get charge getting trapped in the oxide layers. And since the thickest oxide layer is typically the isolation layer, shallow trench isolation, which is modern devices or low cost in older devices, trap would get charged, the charge would get trapped there, and this has an effect in creating effectively a parasitic channel, which causes leakage between devices. So there is this, there's the actual device you want, and then there's this parasitic device which has charge getting trapped, which creates a parasitic channel, which causes current to flow inside the substrate. So this is what you want to avoid. And the culprits here are usually the holes, because the electrons actually move fairly quickly and get and move away from the area. But the holes, they tend to move very slowly through the so-called hopping transport, and then they get trapped near the silicon dioxide interfaces, these deep hole traps, and this is where they then cause the creation of unwanted channels and leakage. And you can see the main effects are, as you can see here in these plots, these are at different temperatures and also different radiation doses, pre and post radiation up to 500 kilorad. You see a decrease in current when the device is on, transconductance will drop, and there will be an increase in the subthreshold, reduction in the subthreshold slope, so more leakage current and low bias voltages, low gate to source voltages. Okay, so one way to reduce this traditionally has been through these so-called gapless layouts, which are or edgeless layouts, where you take a device, a transistor, and you lay it out in a way so that there is no exposed sidewall. So essentially, the drain would be inside one of the isolated regions, and you draw the gate that way. So this would be one way to do it, or this would be another way to do it, and the source is on the outside. The dog bone, or this edgeless dog bone actually variant, is also works almost as well. This was actually very common in older devices, older technologies, where particularly where they had low-cost isolation, where this effect of trapped charge is very prominent. You can see the big improvement here going from a straight gate to an annulus gate. But the problem is, in modern technologies, first of all, as we'll see, TID effects are becoming less important, which is good. And so the need for these enclosed layout transistors, often called ELTs, has decreased. And the second point is that in many technologies, the modern technologies, you cannot draw gates like this because of various layout rules. And so this may not even be allowed. The other thing you might do to reduce TID effects is shielding. But shielding, as you'll see, is a double-edged sword because of the formation of secondary particles. Because anytime you add a material, you're going to create secondary particles. So the point is, will the secondary particles be worse than what you're trying to shield against? So this is an interesting open question. It depends on the type of shield and the type of particle. So you have to be very careful about this. In fact, you might make things worse, because if you slow down something through the shield, it'll actually increase its LET if it's a massive particle, and then you might have more damage later. This is very common when designing, for example, spacecraft shields. You can see the spacecraft skin and all sorts of particles are going through it, and they all create all sorts of secondary particles, which can have worse effects if you're not careful. And there's a large literature on this. You can look up papers on this. I've cited some if you're interested. But here, I'd just like to show one example. So this is for a satellite called Topex Poseidon, which is I just happened to pick this because there's a nice mission dose depth curve that somebody had plotted for this. But the interesting point is, this is the x-axis here is the shielding depth in grams per centimeter square of aluminum. And this is the mission dose for 3-year mission in rads. You can see that, okay, electrons are very easy to shield. Even a couple of, very small amount of aluminum shielding will reduce them. But it's very hard to shield against things like Brahms-Trelleborg or the total trapped protons, and eventually you find that the rate of improvement decreases quite fast. So getting your total radiation dose below about 10 kilorad in this case, which is this horizontal line here, it is pretty difficult given your size and weight constraints. Also, you have to be careful. The most effective way to shield is probably a heavy Z sheet like tungsten or tantalum. But then these will also generate more secondary particles. So you might have to put additional, say, low Z material like aluminum on the inside to reduce this effect. So you often have this composite shielding getting formed. I think I'm running out of time. Let me just quickly talk about single event effects. So single event effects are the other thing that we talked about, the other broad category of effects. And this is any measurable effect that's caused by interaction with a single energetic particle. Heavy ions, protons, neutrons, alpha particles, again, can be destructive or non-destructive. And here's a nice taxonomy of SEEs, which you can find on this very nice resource, which I highly recommend everybody to read if you're interested in this area, which is the TI Radiation Handbook for Electronics, written by R.C. Baumann here, who's a well-known expert in the field. And he's described this taxonomy where you have various soft errors which can be recoverable, non-destructive, things like bit upsets in memory, functional interrupts, and things which, these are all categorized in the single event upsets. Or you can have destructive things like single event latch up, which we'll talk about in a bit, or rupture and burnout. But the basic thing, as we talked about, again, we have an ion track, you have charge getting generated. Now, what happens is when the charge gets generated along the track, some of it will immediately get captured by the electric field. So this will give you a rapid flux in rapid generation of charge within usually a few picoseconds. This we call the prompt response. But then once this electric field has collapsed, this so-called tongue of electric field you can see here, there'll be slow diffusion of charge as well. And this will give you a longer lasting, slow transient or a delayed response. So there'll be a prompt response and this delayed response. And this gives rise to this characteristic SET waveform where you have this brief transient current spike and then this slow collection phase at the end, right? The key point to note is that the strength of this SEE, which is basically proportional to the amount of collected charge at a particular junction, is a function of the cross sections, proportional to the cross section, which is a strongly increasing function of the LET. So the bigger the LET, the bigger the so-called cross section, which is the effective area that is being collected, and then also the path length within the sensitive volume. Obviously, the longer the path length, the more charge will be collected. And then finally, the actual shape will be affected by the circuit response. So circuit, for example, can share charge with neighboring nodes. It can low pass filter this waveform, and so this will eventually affect the property of what happens as a result of these spikes. But essentially, you can see that each of these particles is going to create this particular waveform, a spike of charge, or you can say current, and which will get picked up by affected nodes. On digital circuits, basically, there's two types of things that can happen. So if your SETs are smaller than a critical charge, then they do not cross the logic threshold. They can be largely ignored because of the noise immunity of the digital states. If they're larger than the Q critical, which is the critical charge, they'll propagate through the circuit as narrow glitches, getting progressively broadened. And these above threshold SETs can then cause persistent errors in basically three main situations. Either the event occurs within a combinatorial logic circuit and then propagates to the input of a sequential logic circuit, where it can then get latched by the next clock edge, which will give you a permanent error, persistent error, or the event is large enough to cause rail-to-rail glitches within a clock net, which will then, anything that's connected to that clock net will then get extra transitions, which you don't want. And the last event is what's called a single event upset, where you basically flip the state of SRAM or DRAM cells in any memory cell, thus corrupting the contents of memory. As you can see, an SRAM cell is two cross-coupled latches. So if you exceed the threshold voltage of one of these latches, you can cause the whole state of the whole latch to flip, even when these word line transistors are disconnected. So internally, the memories will get corrupted. Okay, the last point, type of single event effect I want to briefly mention is a single event latch-up, which is a destructive effect, unlike these other non-destructive effects we just talked about. And this is actually well known. The basic cause is well known to anybody who's designed CMOS, is that if you have NMOS and PMOS transistors in close proximity, you have this parasitic PNPN device or a thyristor, which can be modeled as two bipolar transistors, an NPN and a PNP, which are in this cross-coupled configuration, one driving the base of the other, so from the emitter to the base of the other, which means there's positive feedback. The strength of the positive feedback is set by the current flowing through these well and substrate resistors, which decides the VBE and therefore the GM of the device. So anything that causes current to flow through a substrate can cause this PNPN device to trigger, which snaps it back, and you get this latched up state where there's usually a low impedance between VDD and ground if this is an inverter, because the PMOS is connected to VDD and then NMOS to ground, which is bad because you can get all sorts of problems. For example, permanent damage to the chip because of overheating, electromigration, or other catastrophic failure. As you can see, this is a nice picture of a wire that was almost blown up by latch-up induced metallization, electromigration. So basically anything that causes current to flow through a substrate will do this. There are many, for example, electrostatic discharge will do it, but in our particular case, the trigger would be current flowing through from a single event transient. So and that has the potential to give you single event latch up, and just like any other substrate, any other source of substrate current. Okay, I think, and the last point I'd like to finish off with is then what happens to technology trends. Remember that, first of all, due to annealing, the TID that the CMOS circuit, or actually any circuit will survive, can often increase as the dose rate decreases. This is a counteract the enhanced dose rate effects that you see in bipolars. So this is actually suppression at low rates because of more time for annealing to happen. And this actually, and in addition to that, process scaling has actually caused a further decrease in TID effects. Because of the thinner oxides, improved interfaces. You can see that early processes use low cost, which has a so-called bird beak, which used to trap charge, making all the effects of trap charge worse. This has now disappeared with shallow trench isolation, which happened around the 180 nanometer node. And you can see this corresponds to this rapid increase in TID hardness. The x-axis is feature size. Around 180 nanometers when the transition happened, and this suddenly drove an increase in process hardness to TID. On the other hand, SE tolerance has degraded because the critical charge, which is required to trigger something, has decreased because of both reduced supply voltage and reduced nodal capacitance. So Q equal to CV. So if you have a given charge and less capacitance, you just get more voltage. And so what has happened, interestingly, is that TID effects have become less important with time, but SE effects have become more sensitive with time. And today we are in this interesting regime where we don't know exactly what is going to happen. Will this trend continue? This really depends as we move to FinFETs and 3D devices. What sort of new effects will appear, or will these scaling trends continue? And this is what we'll have to find out. More studies are required. So I had a few more things I wanted to talk about, but I think I'm out of time, so I guess I'm going to stop. And I'll just go to my final slide, which is just a conclusion. And I'll just say that understanding the effects of energizing radiation on electronics really requires this interdisciplinary R&D effort. Analytical models generally have limited validity, must be supplemented by things like particle transport simulations. I didn't talk about that, but there's very good software to do it, things like SRIM and others. And then, of course, experiments. And then one point I like to mention, I talked about CMOS, but and fundamentally silicon, but there are devices, there are semiconductor materials beyond silicon which you can use, things like silicon carbide and other wide bandgap materials. They often have higher displacement damage thresholds in particular, pretty important and useful if you're going to do computing or sensing in very high radiation environments. So these are of interest. Finally, again, I've talked about electronics, but the effects of radiation damage on all other system components, such as your integrated photonics or MEMS or packaging, must also be considered while you're looking at the overall reliability of your system. So that, I'd like to thank you for your attention and have time for questions. Thank you.
Perfect. Thank you so much, Jajit, for the very nice introduction in what can happen, actually. So that's been a perfect first talk for this round. Just again, as an information to everyone, please put your questions also during the talk into the Q&A chat. I try to gather some of them to basically ask the speakers after their talks. And also I try to keep somehow in time. So very shortly, I got one question here from John. He says on slide 16, why would only an NMOS but not the PMOS transistor suffer from intra-device leakage?
Yeah, so actually there is leakage in both cases, but typically what happens is with the PMOSs, their threshold voltage increases, so you get less leakage. But it's the reverse with the NMOSs, and essentially because it's the holes that get trapped. So when the holes get trapped, threshold voltage increases for the PMOS, so they get turned off more. But for the NMOSs, you have the threshold voltage decreasing and more leakage. So yeah.
Okay,
but
good.
It's because the holes get trapped, not the electrons.
I got another question from Samita, who asked in the middle of your talk how the displacement damage could be measured in practice, and if it would always be non-reversible or sometimes also reversible.
Yeah, so you can measure it using microscopy. You can do SEM, for example, and look at actual displacement damage. That this is if people do this. And then in terms of if it's reversible, I had this equation which kind of tried to make this point that it's quite dynamic and nothing is actually fixed. So you can have displacement damage happening immediately after irradiation, and then it'll partially reverse with and actually dynamically with time decrease because of annealing. But it could also get worse, and this could happen as a function of temperature. This is what we call anti-annealing. So which effect will dominate, whether it's annealing or anti-annealing, is really quite dependent on the type of particle and the particular radiation regimen it's been subject to. So it's so in other words, there is no final answer for this. It depends.
Good. Then perhaps a final one due to the time. There was one more question from Pang Yan. How would radiation effects be different when we compare silicon carbide, gallium nitride, and silicon devices?
Oh, good point. I was going to show this slide, but I didn't have time. I had this table, which is a nice summary, I think. So these are, you can compare different semiconductor materials. So I have silicon carbide, silicon, diamond, and gallium nitride. The main things you want to compare are displacement energy, which is the energy it requires to create a defect, which is called ED here, and electron mobility, of course, hole mobility. And so what you find is that displacement energy actually is pretty high is the highest for diamond and is a little lower for silicon carbide, and significantly less for silicon carbide as for silicon and gallium nitride. So this will tell you that for a given amount of energy, you'll create the fewest defects in diamond, and a little bit less than in silicon carbide and quite a bit more in silicon and gallium nitride. So it means that you have the most resistance to displacement damage if you're using diamond. And but it's difficult to form junctions in diamonds. So if you're making electronic devices, silicon carbide might be your best bet for something that is very resistant to displacement damage.
All right, perfect. Then I would like to close this first talk. Thanks again very much to Javier, and we are going over to the next talk. And while the slides being switched over, the next talk is going to be given by Dr. Caligaro. Short introduction, Cristiano received his laureate degree in electronics engineering and the PhD degree in electronics information technology engineering, both from the University of Pavia in 92 and 97. And after obtaining the PhD, he moved to a map technology. And in 2006, he actually established RedCat Devices as a startup. During his career, he has mostly been involved in memory design, space application, and also software design for SEE and TID evaluation and open source EDA tools for the same. His research interest is on radiation hardening or radiation hardened standard cell libraries, which are being used in radiation-hardened mixed-signal ASIC, standalone memories, and also testing methodologies for radiation-hardened components. Also holds many patents and wrote many papers. So we're looking very much forward to your talk, Cristiano.
Thank you. I'm going to share. Okay. So, my name is Cristiano Caligaro from RedCat Devices, and my talk will be focused on TID and single event effect in CMOS transistor. So I will briefly summarize what Sumait already said. Then we will move to radiation hardening by design at architecture, circuit, and layout level. Then I will show you some example related to the radar standard cells, radar SRAMs, and some example on analog domain, which is quite interesting from my point of view. So, coming to this CMOS application. As in the previous talk you already known, there are two effects that we have to consider. The first is a long time, the total ionizing dose, the TID. And the second is stochastics, the single event effect. Both TID on one side and single event effect may be destructive. Single event effect may be also non-destructive, so giving essentially soft error. The key point is the whole electron pair generation when we have particles striking in a CMOS device. This is an example of a generic transistor, N channel or P channel, what else. The key point is that insulation in CMOS transistor, so mainly silicon dioxide, may trap holes. This happens at transistor channel level, but also at shallow trench isolation. So we may have holes trapped in silicon dioxide. The effect is what Sumait already said. We may have trap along the channel, in particular on the borders. Having traps on the borders means having leakage path. This means having on the borders parasitic transistor moving the threshold of the transistor itself. This happens both in N-channel transistor and P-channel transistor with the opposite effect. In N-channel transistor, we have mainly a threshold going down. So the transistor becomes leaky, and at the extreme event is that it cannot be switched on and off at all. On the other side, on the P-channel transistor, the threshold rises. So at the end, we have an increasing threshold. These effects are quite complex to be used in a practical application, because if in a digital application, okay, it's a matter of switching on and off a transistor. In an analog device, a small movement of the threshold can be an issue. But not only intra-device leakage, so in the transistor itself, but also inter-device leakage. That means that traps in the isolation can create a leakage path, and transistor of different nature can be biased each to the other. So we can have a leakage path between transistors. The killing effect from single event is the one already explained, the latch-up. This is typical of every CMOS technology, simply because the positive feedback loop represented by the PNP and NPN bipolar transistor may be triggered, for example, by an ion strike having enough energy to trigger the positive feedback loop and then go in the direction of melting the junction. But not only hard error, also soft errors, the same phenomenon create upset if the critical charge, for example, of a SRAM cell, like in this example, is override. We have the bit flip. If I have stored a 0, then I have a 1 because of the passage of ion strike or what else. As already said, ion strikes may have different impinging angles, so creating and causing a complex transient. But at the end, the effect is always a spike of a current or a spike of voltage, and in case the transient meets some flip-flop or latch, it can become an upset. So these are some example of effect on coming from radiation. The main one is the single event transient, which is the temporary bit variation. This is valid for logic and for sequential cells. We have the upset, which is the real bit variation in a device. The multiple bit upset is usually in memory when we have more bit varying their content because of a single ion strike. Or we may have multiple chip upset, cell upset, which is related typically on memory. Single event functionally interrupt is typical of microprocessor, microcontroller, state machine, and this represents an error requiring usually a reboot of the device or something similar. Then there are many other kind of upset. So how we can mitigate everything? I talk about mitigating because resolving at all the problem of effect of radiation is quite hard. We must, of course, consider that we can reduce the probability of having an event on a silicon device. And of course, we have to reduce the impact, try to mitigate at the minimum the effect on silicon device. Mainly, radiation hardening may be done in 3 ways. By process, that means having some specific manufacturing process. By shielding, for example, using also some specific package, or by design. By design is quite common, in particular in this year, the quite common solution for making a radar device. Of course, this can be combined. We can use, for example, a hardened process and use also some techniques coming from the radiation hardening by design. Radiation hardening by design in CMOS, just to stay in the talk of this webinar, means that we only use strategies related to how to design the device. Which are the advantages of using radiation hardening by design on CMOS? Mainly the maturity of the process and the high yield of the node that you are going to adopt. Low cost. This is, of course, compared to radiation hardening by process. Customized process for radiation hardening are quite expensive. Another advantage is that we have many foundries able to provide more or less the same node or different nodes. This is a good point. Also the multi-project wafer approach, because we can make a fast prototyping and also low volume production. You must consider that making space chips is not something for the large community, it's for few applications, so we do not have big numbers, and low volume production is a good approach for making such devices. Another thing quite important is the portability, because if you use some specific techniques on one process, maybe you can move to another process. This, of course, requires some fine-tuning when you move from one node to another node. But at the end, this is a good recipe to move to the market for this kind of components. Radiation hardening by design is divided in 3 levels: the architectural one, the circuit level, and the layout level. The architectural level, just to make an example, maybe this, for example, a memory. A memory is an ensemble of macro blocks, and you have to consider that a good strategy of building blocks must be considered. For example, just to make an example, if you have a state machine inside your device, well, you have to consider that single event functional interrupt may occur. So trying to avoid forbidden states. For example, if you have a multiple bit upset, you can make some kind of redundancy, and so on. So the architecture level is the starting point when you make a radar chip, and is strongly related with the other levels. This is some example. For example, in a memory, if you have to avoid multiple bit upset, well, you may divide all the bits and have a replication of the decoders for each bit, or part of the decoders, of course. This is in the attempt to reduce the multiple bit upset on single event upset. So to avoid that one ion strike can give more bit upset. Another example is a redundancy, the ECC, just to intercept and correct eventual upset. And last but not least, the wide use of voting methodology, also TMR approach is called. So if I have a decoder and I have an ion strike, I have a redundancy that provide me the right value. There are many of these things. And on top of all, there should be also a behavioral radar by radiation-hard description. So if you start from a Verilog or VHDL, also these codes must be considered to work in a hostile environment like this. Circuit level. The circuit level is, for example, trying to enhance the resistance of, just to, as you can see here, of an SRAM cell. The goal is to increase the critical charge, to reduce the probability that you have an upset. In this case, for example, placing a capacitor in some point, you can give a little increase of the critical charge. In radiation hardening by process, there are some masks making this job, of course, but if you stay in a standard CMOS process, this is something that you can build using, for example, a fringe capacitor. Or you have the opportunity to increase the stability to transient of logics, for example, making some internal redundancy at the transistor level, for example, a 60 XOR gate into a 10T XOR gate. These are small things. There are many of these. These are only just to show you the example. The layout level is the one, is the most important, of course, but you have to consider that it is strictly related to the other levels, because you can even make the best layout of the world from the point of view of radiation, but if you have the wrong architecture or the wrong circuit approach, you may lose also your solutions. So this is something that you have to consider at all levels, not only in the core of the chip, for example, but also in the I/O. The I/O of a final chip, of course, are under irradiation as well. So they have borders, they have inter-device and intra-device leakage and so on. So also paths must be considered. In principle, if you design a radar component, you have to do for all, for everything. Let's show some solutions. For example, for the single event latch-up. The single event latch-up, the problem that I showed you before, for example, may be solved using a biasing. You place in the middle a biasing on VDDs on the end well and GND on the substrate. In this way, you cut the positive feedback loop. And not only you cut the possibility of triggering the positive feedback loop, but you also mitigate eventually the inter-device leakage. Remember the presentation before, there was an overlap between TID effects and single event effects. Well, this solution can go in both directions. I mitigate the probability of triggering a positive feedback loop coming from an ion strike, but I also mitigate the leakage effect between different transistors. This is a solution for single event latch-up. For the TID, well, Sumait also show you, we can use, for example, the edgeless transistor. This transistor is very effective because you still have the border, the effect border, but the border is in a region where there is the same potential, so it has not effect. The drawback of this guy is that we have an asymmetric device, so area and perimeters are different, and this must be considered not in a digital application but in an analog application. Of course, you have to consider that drain and source may be different. So, to summarize the techniques before moving to some example, radiation hardening by design is essentially a set of techniques. There are many techniques, I show you some, but there are many. And each technique works at a specific level. For example, at architectural level, I expect to solve the major part of safety problems and MBU. At layout level, I expect to work mainly on TID and single event latch-up. So all these levels are works together. But of course, at architecture level, which is the starting point, the focus must be on soft error in terms of functional errors. Of course, since there are many of these techniques, they are fine-tunable. So the point is, first of all, try to consider which is your application, because you may have, for example, in space, different orbits, different radiation environment. For example, low Earth orbit require less TID resiliency. For example, a deep space mission require higher TID. So these techniques must be mixed and considered before starting with a specific application. So let's see what happens in standard versus radar transistor. On the left, you have a traditional inverter. And where are the problems? The problems are on the border, in the N-channel transistor, for example, here and here, on the P-channel transistor, in between, because there is no guard ring in the middle. So we may have a single event latcher here. On the right, you see a transistor shielded for almost everything. This is the maximum that you can obtain. So you have in the middle the shielding between N-channel and P-channel region, and you have the annular transistor, the edgeless transistor. The drawback is evident. Usually radar transistors are quite larger than standard transistors. This is an example. On the left you see an inverter, on the right an N port. The penalty is quite high, but again, because I'm considering in this case the best of solutions for making a radar device, you may relax something according to the application that you are dealing. This is another example. This is a 180 nanometers inverter logic. On the right you see the layout, on the left the schematics. Of course, you see that the edgeless transistor provide some complexity that you have to consider in calculating the length and the width of the transistor. So this is something that you have to consider if you use tools for DRC and LBS. But this is something feasible. You can handle these things. Making the transistor itself radar is not the end of the job, because of course you have to consider also the border outside the transistor. So you have to use some end cap, corners, closing elements, all things that of course if you make a digital design that must be placed at place and route level. So this means that these borders must be placed to close the region, to obtain an N plus guard ring, for example, here in the P-channel transistor, or a P plus guard ring in the N-channel transistor. So biasing the N wells, all the N wells, the substrate. This is quite important because you have to consider not only the inter-device leakage at local level, but the inter-device leakage also outside your placement. And this is an example of a place and route of some cells that are enclosed in their specific region. There are different strategies on different nodes. Sumait before correctly said that with the modern technologies, TID is becoming less problematic. We divide in mainly three regions. The submicron region is the one down to 100 nanometers. And here probably making annular transistor, edgeless transistor is convenient. After this, probably not, because the oxides, at least at intra-device leakage, are good enough. So not only because silicon foundries do not like that you make annular transistor DRC start yelling if you design something like this. But also because you have not particular beneficial on your application. I mean, at least for space application, where we have to deal with up to 300K rads. So in this region, we call deep submicron region, down to 20 nanometers, making annular transistor probably is possible. In 65 nanometers, sometimes we make some half annular transistor, but it is not particularly convenient. It depends on the application, of course. In 40 nanometers, 28, 22 nanometers, you can avoid making any edgeless transistor. This is a waste of area, a waste of time, probably. The border of 20 nanometer, the boundary of this, take to the ultra deep submicron region. Ultra deep submicron is the arena where you can find FinFET and others. In this case, well, I don't know so much because it is still something that we have to consider. I never worked on radar application with FinFET, only for other application, but probably what we expect is to have a very good TID, but some problem on soft error because the technology is very scaled, critical charge are very low. There are effects that we are not considering. Of course, there are many studies ongoing. Also, from the European Space Agency, there is an effort to understand what happens with such technologies. And of course, this is a knowledge that we have to build. After that, we can make some solutions at the layout solution and the device solution. Coming to memories, this is an example of a full radared memory. This is a 60 cell, fully shielded. As you can see, there are annular transistors almost everywhere, and on the right you see the fringe capacitor on top of the cell. Of course, this is a particular example. This cell can resist up to megarads, but of course, it takes a lot of area. So this is something that are for some very specific applications. A compromise is this one. This is an SRAM for embedded application. This is, we do not use at all edgeless transistor. This is a 180 nanometer process, but at least we try to place some biasing for every cell. Usually this is not done in traditional memories, but in this case, better is placing substrate and well biasing on each cell, just to avoid latch up. Of course, you may have some upset even at low LET. This is the equivalent cell for dual port SRAM, so 80 cell. The strategy is almost the same, as you can see, and these cells are quite resilient. Well, are resilient from the total dose point of view because the degradation is contained, and the single event latch up. Of course, some soft error arises, but in that case, you can use ECC to mitigate the effect. At the architectural level, which is the most interesting from my point of view for the memories, the approach is to try to shield as much as you can the part related to the coding. So the input buffers made probably with annular transistor, row decoding and column decoding. This is an example of a block, memory block, 1-bit memory block. The ensemble is on the right. As you can see, they are placed each close to the other, and they are independent from the decoding point of view. So each of this block has its own decoding. So if I have an ion strike on the first module that decode the wrong cell and provide me an upset, well, this is not propagated to the other cells. This is a very easy and practical solution, but of course requiring some area, because the array is not monolithic. You have, of course, more logic for making the decoding. Another thing to be considered is the clock tree. If you have a synchronous memory, of course you have to take care of the clock tree in the module. So in these cases there are filters for making a clean clock moving into the device, and try at least to have a short branch of clocks going into the device. Now, I want to share with you some examples of analog devices. This comes from a recently closed funded project by the European Union among the Horizon 2020 effort, where we designed, the goal of the project was to make a microcontroller for space application. We designed some analog block, including this one, which is a DAC, a 12-bit DAC, so not so straightforward. The process is 130 nanometers. And as you can see, at architecture level, we choose an approach which is quite unconventional for this number of bits, which is the resistive approach. Usually, with such bits, 12 bits, current steering or what else are preferable. But the problem of current steering is that they are based on current mirrors, and the current mirrors are prone to degradation under TID. So we decided to use the resistive approach, mainly because we used polysilicon resistor. Polysilicon resistor are very stable under the radiation, so TID is not a problem. And also from the single effect point of view, they are very good. So we used a specific architecture with coarse and fine conversion. If you are interested, this is the reference of a paper we wrote some months ago. And at circuit level, we moved outside, so we used standard cell radar for making the decoders of this guy. And also we made a customized layout for the output buffer. We tested this one. The architecture is very stable. And up to half megahertz it goes quite well. Some details on the solution. For example, this is the poly array, resistive array, and this is the ELT switch array, because of course every resistor have its switch driving it. And you can see here, top right, there is the annular transistor for N channel and P channel, and dummy elements in the to complete the layout. Dummy elements, these are mandatory, of course, when you make a chip before sending to the silicon, because you make the dummy field procedures to planarize the process. But in our case, we prefer making our own dummies, because we don't want that dummy field procedures touch our design. So in particular for this part related to the resistive matrix, we took care of making our own dummy field before running the dummy field to send to the silicon foundry. This is an example of the buffer. The buffer, as you can see from the circuit level, is very easy. We try to use the easiest solution that we could find, and make leverage on annular transistor placed, as you can see, in this way. This is the differential pair that you, from here, you can see here, and made all with annular transistor. So this is quite stable. Of course, the matching is not comparable from the matching that you use for a stacked approach in a traditional transistor, but you can obtain good results in any case. The second example that I want to show you is related to an ongoing project that we have with the Italian Space Agency. This project is funded by the Italian Space Agency. The goal is to make a radar point of load, and the expected target for us in this case is the deep space. Again, from the architecture point of view, we have the operational amplifier here, and the output is somehow a power application, because this one is expected to drive up to 20 milliampere. So the internal solutions that we adopted in this case is to use, again, from the differential pair, an annular transistor designed using a common centroid fashion, and of course, as I told you before, to use also dummy structure around to compensate eventual drift from the manufacturing. The 180 nanometer process is, of course, very stable. So it's not particularly complex to obtain a good matching, but of course it's not exactly what you can obtain with ELT transistor. The final one that I want to show you is the sort of power unit. In this case, you see this NMOS. This is an NMOS transistor, but it can be also a PMOS. It's more or less the same things. And all these organ pipes that you see here are shown in detail here. You see annular transistor, very, very stretched, but still designed to be to follow all the rules that I've told you before. So from my point of view, I have finished. If you have questions for me, it's would be great if Maurits can tell me.
Yes, perfect. Thank you very much. So I'm going to start with the very first one. Let me just basically open that up. Sorry that my light's blinding again here. The first one was, kindly explain the software architecture that can be incorporated to overcome radiation effects for complex computing elements like microcontrollers. Well, that was a very early one when you just started your talk.
Yes, yeah, because software architecture, I suppose the question is related to having a good VHDL or Verilog code before starting a device. This is, I suppose, yes. I'm not an expert on this, but there are some few tricks. For example, at behavioral code, you can also just include TMR flip-flops. There are some special cells inside the code, and you may intercept these cells and make it to be used in your design. Well, probably this is not exactly the behavioral code, but the synthesis. But of course, at synthesis level, you have to intercept and use the right cell. At a level higher level, at the behavioral level, the code must consider to avoid using forbidden states, to keep everything under control, to use counters that cannot skip from one number to another one. So there are many tricks. Probably Fabian, talking after me, will mention something about this. They are expert in this field.
Okay. Then Core has a question here. I'm just reading it. Is it correct to state that for future advanced semiconductor technologies, say 5 or 3 or below technologies, the further radiation hardness improvement, if needed, would mostly come from basically design rather than improving the radiation hardness of the technology itself?
I lost the first part of your
The
question.
idea is when we're going to really fine line CMOS, let's say 5.3 or below technologies, the question is, will the further improvement in radiation hardening come mostly from design rather than radiation hardness of the technology itself?
It's complex to do. It's a good question, but it's complex to give an answer because in very scale technology, sometimes we don't know the real effect, the impact that they have the effect. At the moment, what we can state is that total dose is becoming to be not an issue. But from the soft error point of view, yes, there is something to be considered. This can be done either from a circuit, from the circuit level point of view, but also from the coding of your application. The technology, probably FinFET are more stable, but it's not clear how is their behavior from the soft error point of view. Probably also single event latch-up will become less problematic than in the past because, well, the critical charge is lower, this is true, but also power supply is lower. So at the end, probably there will be a sort of balance, but it's quite hard to say. We know very well submicron and deep submicron and their behavior, but not for this new technology.
Okay. Then I have one more, which I want to read out loud from Jorge Marin. I would really appreciate if you could provide some information on how you model and simulate SEEs in your analog designs.
Well, usually what we make we make simulation. This is called fault injection, in particular for memories. What we simulate is the injection of a current. This can be easily done using a SPICE-like simulator. For example, we use XICE from Sandia Laboratories, which is pretty good and pretty flexible for making such kind of simulations. On the other side, touching the model from a foundry is always something, yes, you can do this, but it is at your own risk because the foundry usually give you the model package. This model package is the result of many measurements on their silicon. Going and touch the model is something that you can make maybe for the threshold voltage, but not for the other stuff. So in principle, the good idea is making extensive simulations, trying to move for the total dose point of view, for example, only the threshold, and for the single event, injecting current, making some fault injection analysis. This can be done.
Perfect. All right. Then for keeping somehow a little bit of our schedule, I would thank Cristiano very much again for his talk. Thanks a lot. Also, I would like to ask all authors or speakers who have just finished their talks, please look into the Q&A chat and those questions which I did not read out loud, perhaps you can just answer them if you have the chance in the next, I don't know, minutes, hours, while the others are still talking and giving their presentations. Thanks a lot, Cristiano. Then we can switch over to Fabian Vargas. I'm already starting with his CV. Dr. Vargas obtained his PhD degree in microelectronics from the Institut National Polytechnique de Grenoble in France in 1995. He was then a researcher at the BR National Science Foundation in the upcoming more than 25 years. And at present, he's a senior scientist at IHP, the Leibniz Institute for High Performance Microelectronics in Germany. where he works on the design of on-chip sensors and cross-layer resilience for aerospace systems. Dr. Vargas holds many patents, published over 200 refereed papers, received several awards, and is basically involved in many societal activities. And then the floor is yours, Vargas.
Can you see my slides and my audio is okay for everybody? Perfect. So first of all, 1 second to thanks to Daniel Moritz for this brief introduction and make available all this infrastructure for this webinar. Also to Cristiano for coordinating the invitation of HP. And before going directly to my presentation, just a quick comments about how can we design software robust for space variations or things like that. Quickly, because this is not the goal of this talk today, we can use software diversity. So try use the same specification of software implemented by different design groups. So we have different implementations of the same specification. And if possible, combine software diversity with hardware redundancy. Then you minimize overheads. So this is one possible direction of how to design software robust for critical applications in general. For the robustness of FinFET, I could make a comment on that because we performed some simulations on FinFET. And one of the things that we can do is make a variation of the number of fingers in a FinFET. And this can play directly an important role in the robustness of the FinFET for single event upsets. The number of things, and not only the size, the volume of the sensitive regions of source and drain. Just a quick comments. But let's go on that. Let's go. It's time for my talk now. So, on-chip infrastructure for silicon mode monitoring, emission mode monitoring of resilient systems towards silicon lifecycle management. The idea is go from silicon to operating system level. So this is a general overview of everything. For more detailed questions or those that are interested in deep discussions, I will be very pleasant to answer messages, emails, and be contacted later after this talk. So let's go for the first statement that I think everybody will agree. Simulation and measurements can never tell the whole story of how devices will behave in real world use. This is a little bit scary, but I think everybody agrees with that. So, for instance, let's go. In real world environment, real world, we have various types of interferences that can occur simultaneously. For example, total ionizing dose, several environmental conditions, extreme temperature, space radiation, battery wear out, stability, noisy on power supply lines induced by electromagnetic interference, electromagnetic emission, aging induced by wear out TDDB, hot carrier injection, electromigration, single event effects, and so on. So it's difficult to predict all these during the design phase. And when you think that you understood everything and included everything in the simulation, we have one more problem. It's dependent on the applications, the workload. If you change the workload, you exercise different parts of your circuit or your system. So the sensitiveness also change. Maybe, so it's totally unpredictable. So it's very complicated. And to conclude this slide, there are many standards you can find in the literature to certify circuits and systems, but all of them are applied independently, very important, applied independently on fresh devices, not taking into account the combined effects one phenomenon may take over the other one. So nobody is obliged to do combined effects experimental validation because there's no standard specifically for that. This complicates even more the scenario. So let's try to answer a little bit these questions on the next slides. First, the focus of the talk. So these are, I took this from the internet 2 months ago. For more than half a year, internet found the root cause of cores I 13,000 and 14,000 that failed in the field. So this was related to the clock tree circuit within these 2 generations of ICs. that was particularly susceptible to aging under certain critical operating conditions, more precisely temperature, voltage, power supply voltage, and clock frequency. BIOS settings that should be defined by design, by factory, failed to limit VDD and clock frequency when detected high temperatures by the on-chip sensors. So this was a, let's say, a naive problem, but complicated problem that was found by Intel, published on the internet, and apparently solved it, or on the way to be solved. So wouldn't it be great if we could keep on analyzing our IC designs once they are in the field? That's a good question. And facing this always challenging context, this talk will give us an insight on how HP addresses the design of ICs through the use of embedded monitors and sensors, and how we can enable a range of new in-field optimizations throughout the silicon lifecycle of these circuits. Okay? So, first of all, what is going around in terms of in-field on-chip system status monitoring all around the world? What has been done so far, Who is doing that? There is a lot of companies and research centers working on this topic. Please excuse me if I don't include all of them in this slide, but I just included just a few of them that I consider are very important, and then in some way we have collaborated with in the past. And now we are still collaborating with some of them. So first of all, Synopsys, they proposed their Silicon Lifecycle Management, SLM platform. Then you can find also Siemens, Tessent Embedded Analytics Solution. We have also Proteantex from Israel, on-chip monitoring and deep data analytics, the Proteus platform. Now it comes with HP Microelectronics, on-chip sensing analytics for lifecycle management, SLM platform as well. But we find many other companies and research institutes, as I mentioned, in the world working in this topic, or at least part of this topic, on sensors, on information collected from sensors and then interfacing this, manipulating all this information, or in the analytics on chip specifically. But more or less, all of them are related with this topic. And here we have Intel and AMD with machine check architecture, ARM reliability, availability, and serviceability management, RAS management, Seagate uses for their hard drives, self-monitoring analytics and reporting technology, the smart technology. Cisco systems that use silicon-based sensors for reliability, for system reliability prediction. These sensors are not on chip, the sensors are on board. But anyway, they go in the direction of lifecycle management with that. So very interesting work they have been doing in their routers. Also, we have Testonica and Tautec. Testonica is a company in Estonia, and Tautec, the biggest university there in Tallinn. They are working on the interface between the data collected from the sensors and the analytics algorithm. So they collected information, check, validate the information, format, store, add some timestamps, and store this somewhere. So they're working in the interface, hub interface for that. Also, Karlsruhe Institute of Technology, KIT, and Synopsys, they are working on electron migration sensors, on-chip sensors for detecting electron migration, as we are doing as well some work in this direction. But they have published nice work on electron migration sensors for memory, for memories, on-chip sensors for memories. In the list, I could also include the University of Hamburg and many other works that we can find in the literature, but so that's it. Now, one slide specific for Synopsys. They proposed the Silicon Lifecycle Management platform. First of all, they have process voltage temperature monitors, PVT sensors on chip. Also, they have path margin monitor as they define it, but this is in other words, behind this, this is an aging sensor. They call it a very nice name, path margin monitor. And then all the information is collected from the sensors by a connection fabric using NAMBA protocol. These digital interface wrappers, they have also controllers dedicated for this activity. They validate, they format, and they store the collected data and prepare the data to be analyzed by analytics processor, RTM, which is a RISC-V processor, running Zephyr operating system, open source, to perform in-field analytics. I would also suggest for those that want to work in this domain or this level, Synopsys ASIC designer CAD tool for AI accelerators. This is a very nice tool that you can use. Synopsys proposed using this tool specifically for synthesize the processor and profile it according to the analytics code. This is a very good idea. You should try that for those that are interested. For Siemens, propose the Tessent embedded analytics, where we have transactions between processors and memory that can be monitored by hardware IP blocks. They have more than 20 IP blocks designed specifically for this task. RISC-V accelerators, okay. So these are, and what is in red are the embedded IP blocks, more than 20 in this case. They can be configured at runtime to capture trace data and interact with embedded analytics modules. Very nice proposal. Data from on-chip sensors are processed locally or sent to be processed outside in an external tester or the cloud eventually. But anyway, can be processed externally. They have the option to go outside from the XAI JTAG, USB, TPIU, for example, units that can be used to output all the data collected from the sensors. Also, the message infrastructure is separated from the system buses to minimize or to avoid at least performance loss. For example, the status monitors, they are used to monitor any circuit within the system on chip, like a logic analyzer. But instead of sending outside all the collected data from the sensors, they use the processor analytics to do so. They have also the trace receiver that collect and format all the information collected from the sensors, encapsulates in the Tessent analytics messages, and send it outside the chip to be processed elsewhere. So very nice proposal. You should know this is a good option for those that want to work in lifecycle management. So we have Protean Tex, which proposes the Proteus platform, monitors IC through lifecycle, design, characterization, qualification, production, and in-field operation. So the whole process from design to in-field operation is very interesting. They cover everything. Reports on IC health and performance at the above, every stage, one of the above indications. So comprised of custom IPs, they call agents, embedded ICs, and also cloud machine learning based analytics to perform the analytics on cloud. So you can do this on chip, but they propose to use this on the cloud, where they upload the millions of simulations. Since from the design phase, they collect information from the characterization and manufacturing process. All the data collected by the agents are uploaded to the cloud and then use it to machine learning purposes. Very interesting solution. So they have several agents on chip sensors for that. Margin agents, which are, in other words, aging sensors. Operational agents that monitor the environment, the workload, like the switching activity, power supply noisy, clock characteristics like jitter, thermal stress. So this is strongly dependent on the application, the workload. So very important. You cannot do that during the design phase or validation of this the design or during production test. So this is very important to go in the field to get this information. So design profile agents also monitor electrical parameters like the threshold voltage of transistors, a specific set of transistors, NNP are selected for monitoring thresholds, IDT, transient current, quiescent current on the IC, and this is mostly related to production test. That's important for in the field monitoring. So they have also high bandwidth memory agents, very interesting, monitor that is connected, that monitors signal integrity, degradation per pin pairs. For example, you have the input and output pins of an interposer between the processor and the memory, and then you monitor the ends of this connection to detect electron migration, signal integrity, and signal degradation during life cycle. Once this is detected is beyond the quality levels expected for that application, then during not user times, or at least expected maintenance cycles, you can replace by redundant tracks and lanes in the interposed layer, for example. Now going to HP, where HP is situated in all these contexts that we have addressed so far. So if you take synopsis, they are strongly devoted to measurements of PVT and path margin monitors at the silicon level. If you go to Siemens, they go for transactions, mostly towards transactions between IPs and peripherals. If you go to Protean Techs, they do both, from silicon to transactions. And in the case of IHP, we go also from silicon, our chip sensors, all kind of SCU monitors, single level chaps, transients, temperature, all kinds of sensors are monitoring power supply activity, as you see later. But also we are interested in monitoring real-time operating system level transactions to guarantee mixed critical execution. So this is, let's say, a big difference and good contribution that we do. We are performing, we are targeting for the market. We are the only ones so far, at least we understand, that are working in this direction and try to combine sensors that on-chip sensors that monitor operating system activity. I give more details in the next slides now. So we call this as cross-layer sensing. And so the idea, as I said, is processor operating system activity, specifically to guarantee time and space isolation, task criticality, integrity, scheduling algorithm independent. So this is strongly dependent on the algorithm used for scheduling. The final end is guarantee compliance with ARINC, the standard ARINC 653 for avionics application software standard interface, which guarantee hosting of multiple applications of different software criticalities running in the same hardware platform. That's the basic idea behind this. So we are strongly concerned with that. One slide to summarize the basic approach that we are considering for lifecycle management. So we have the integrated circuit, the cross-layer sensor from silicon to operating system. So we collect the data, specific interface. We go to silicon lifecycle management engine. Then the engine operates on 3 stages of silicon lifecycle. The first one is during IC characterization. Then we estimate the IC lifespan using stress testing, wear out testing, high temperature operating life tests, burn-in, IC reliability, SU, single event latch chaps, TID, EMC. So all this information is collected and stored in memory for later support analytics on chip. So we have during production IC screening process, signal times lag. So we monitor signal times lag in this case, in critical paths, operating voltage, minimum operating voltage, IDEQ. This information is also collected and used to make this available for on-chip analytics later in later processes in the field. So we call this the offline phase. Then we go for the online phase, in-field operation, where we optimize IC towards the user needs of lifespan, performance, power, reliability, and security. So it depends the case and the moment. In the beginning of user of IC operation in field, we could privilege performance, then later optimize for power, and vice versa. So we treat case by case on the fly in the field. And also, as written in red, our let's say, most important contribution, we monitor operating system faults and application faults depending on the algorithm that we have used, we have specific on-chip sensors that we call watchdogs for this purpose. Okay, so let's go. Next one, a little bit more detail. So for the application processor, our approach is processor agnostic, but in this case, to illustrate this slide, we considered also a RISC-V processor to illustrate the approach. We have also manufactured some sensors embedded in the RISC-V processor, so it can be a RISC-V processor, where it runs under the control of the Zephyr 3.7 operating system or FreeRTOS. Both of them are easy access from the open source community. So very interesting. We are all motivated for using these operating systems. Also, Synopsys use this one, by the way. Then we have the cross-layer monitors from silicon to real-time operating system, collecting information. Then we go for the interface with the collected information, and then we validate, because not all information collected from the sensors are valid. So we have to check if it's okay. Then we format it, then we store this in a separate memory and make it ready for analytics algorithm that comes in the sequence. But before we have an output signal, only one pin from the die or from the chip, depending on the level of abstraction you are. This is just an error indication. We have a problem, okay, not okay, gonna go for the system, okay? At the same time, we send this information for the lifecycle engine. How we implement the silicon lifecycle management engine? So we have several options, at least two, very clear. Traditional hardwired, an ASIC processor, an ASIC hardware can be implemented, specified from the analytics and control algorithms. Or we can use a more flexible architecture like an ASIC, application-specific integrated processor, software programmable, privileging late functional changes. So that's the option that we have selected. Since Go was for lifespan, power reliability can change during operation in field. So if you have a hardwired ASIC, it's more complicated to change. So we go for ASIC. That's our choice. So as an ASIC, we are using the RISC-V processor for this case. This is our target processor. And but this processor has been profiled for the analytics code and control codes that we run in the processor. So we implementing in hardware only the instruction set that you really use it by the analytics code. Otherwise, it's not compiled. And talking about the compiler, we use the Zephyr or FreeRTOS. So the compiler also must be adjusted for this new hardware. So this is the next step that we have been working with. For the analytics code, to give an idea what can be used, machine learning models or mathematical or modeling techniques based on integral linear programming, statistical outlier methods, lookup tables. Lookup tables is a if, then else. So it's very simple. If you don't have enough information, you cannot perform on-chip analytics with machine learning. You cannot train a neural network with that. So you should use simple algorithms like lookup tables or outlier methods. They work very nice and they provide good results. Requires much less hardware, by the way. And so all these codes run into the profiled RISC-V processor. Then we have the control block and the actuators on the system. So we control PLL, power supply activity, including power supply VDD. So including, we can increase or reduce proportionally if you depending on goal, if you increase performance, maintain performance, guarantee lifetime, because we are much worried about aging, so we reduce VDD. Depends on what you're looking for. One slide about HP. So we have our clean room. We work with one of our technologies here is 130 nano silicon germanium BiCMOS radiation-hardened technology. It targets high-end products, high-end applications with low volume market introduction and potential mass production for commercial fabs if you want to migrate to another foundry. But we can provide very high-end chips in this very mature technology. for specific applications, in particular case space. This technology also being qualified, being evaluated for inclusion in the ESA European Space Preferred Parts List, EPPN. So we are expected to conclude this process next year. We started during the COVID times, but as you can imagine, we had some delay because of that trouble period. So now we are concluding this process next year to make this technology available on the EPPN. For our R&D, we are basically targeting embedded systems architectures, embedded systems architecture for space applications. That's the main goal of this talk today. Not necessarily, but this is one of the most important areas of research. Our clean room, 1,800 square meters. It works 27 hours, 7 days a week, including area for enabling wafer interconnects and chiplet integration. If you want to get more information, fresh information, please feel free to access the IHP webpage. It's updated on the daily basis. So now, in terms of on-chip sensing, what kind of sensors have been researching, implementing, and validating in IHP? Quick overview, 1 or 2 slides on it. So, on-chip sensors, aging, the first one, the most important from my understanding. So we apply aging to detect the delay in critical paths in combinational logic. SRAM IP core, so SRAM blocks are also monitored. The time response of memories as function of aging is collected by the aging sensors. This is a collaboration with Synopsys, where we have integrated our sensors in a Synopsys embedded memory IP block, designed with 5 nano TSMC FinFET. There's a publication on that to read a little bit about. This is a very fresh work published this year, 3-4 months ago. Also PLL, we are developing some on-chip sensors to monitor aging of PLL, voltage controlled oscillator. As function of radiation deposited TID, the output of the voltage oscillator, voltage controlled oscillator, is reduced by almost 0.2%. So these can be observed for 1 megahertz deposited. So it's a high dose rate deposited 1 mega, but 0.2 shift in PLL output. This means that the circuit can start experiencing some synchronization problems. If you go into deep space electronics, this is very interesting. Lower orbits is not necessarily 1 mega, but if you go far, yes, it can be a big problem. So after calibration, it's important to say that the aging sensors can be used for device screening during process, device screening process during manufacturing, production. And in addition to aging, we also detect SEUs in flip-flops and SCTs in combinational logic. These sensors can be combined with a different version, a more complete version of triple modular redundant flip-flops with self-correction mechanisms. So it's a clockless solution with 0 latency correction and transient filtering in combinational logics. So we call this delta TMR approach. And so the same sensor used for aging can also be used for single event upset detection and transients. So the same sensor placed at the output of the critical paths can detect both aging or in that path and also single event upsets and transients. And also electromigration, the same sensor can be used for that. Some types of electromigration that increase delay are liable to be detected by the aging sensor as well, in particular memory. Temperature sensors also have been developed, power supply activity monitors. We have been working on that. We are targeting some standards for this. So we can detect IC standards 61004/29 and /11, for example, 2 specific standards that are liable to be detected by this kind of on-chip power supply activity monitor. And we published also last year one approach that uses neural networks to classify the type of noise arriving in the power supply bus of a given chip. So we are on the direction of a very nice work where we combine the on-chip sensors followed by the analytics performed by AI on the type of noise. Soon will be new publications, fresh publications in this topic. Also, current sensor IDQ can also be used to monitor TID effects, for example, on electronics, and also aging as well. Some cases of age that increase IDQ can also be detected, but in particular, TID can be detected with that. How can we integrate the sensors at the system level? So first of all, we define the functional units working in the same time domains, same frequency times lags. For example, floating point multiplier, floating point adder, level 1 cache for data and for instruction. And once this is done, we add the aging sensors appropriately at the output of these functional blocks. It can be several sensors per functional block, 32, 64, depending on how many outputs we want to monitor. Then we compact all these sensor outputs using our management hub that collects, validates, and formats all the coming data from sensors, and provide 1-bit error indication output. At the same time, we collect all this information because all the information stored in the memory mapped information. Then we can, and these registers are connected by SCAN, JTAG, ITAG can be used to read out all the sensors if you want to perform diagnosis later. So once we detect an error in the chip, then we can scan out all the sensor outputs and identify exactly which was the functional block that failed and which path inside which functional block we observed aging degradation. One or more of the paths, for example. Okay. Sensor safety features. We have added also some saboteurs into one of the critical paths that intentionally increase delay to test the sensors before using the sensors to measure periodically, not online, but periodically we monitor delay in this case. And also use power gating to prevent self-aging. So once the sensor is not used, it's power gating is on, and so the sensors are not powered on. So saving the sensors from getting old. So this is a very important procedure that we use it to prevent aging of the sensors themselves. We have also manufactured the chip. So we integrated 64 aging sensors in a RISC-V processor, Basilisk, in a collaboration with ETH Zurich. So we just received this process from our manufacturing here in the clean room this month. We added the 32 aging sensors at the output of the floating point multiplier and 32 sensors at the output of the level 1 instruction cache memory. As we see here, 32 sensors for the group 1 floating point unit and 32 sensors, aging sensors for the memory connected to the bus. So in between the memory output and the processor bus, we connected the sensors there in parallel with the original flip-flops of the memory, output flip-flops. Okay, so Basilisk was designed using our technology, 130 nano silicon germanium. We used for that our OpenPDK and multi-project wafer as well. So you have access through the web. In this link, you can also access our OpenPDK. We have also OpenPDK for radiation-hardened library next year, probably because this is a new project that we start this year. So next year, we're going to have an OpenPDK for the radiation-hardened library. Not the same one as we have the commercial one, but there's a good one enough to make it available on the OpenPDK for the radiation-hardened. If you want to read more about the Basilisk processor, you can access the ETH Zurich to have more information about the RISC-V processor. And basically, the dimensions of the chip is almost 35 square millimeters, 3 million gates, 1.2 volts, and very, very important, area, power, and delay are negligible. Negligible because of sensors did not change the original processor layout. In other words, we added not used the routing space. So the logic near unused areas were moved, pushed back, and then we had the sensors in those places, or we had the sensors directly in unused areas. So in other words, we didn't increase area. And the sensors were placed in parallel with the original flip-flops at the output of the critical paths. So we did not replace or move the sensors, but we added this in parallel. So this can explain a little bit why we have negligible area power delay for the addition of the 64 sensors in the whole processor die. So far we were talking about silicon level information. Now we go into system level information. Okay, so we go up a little bit higher, and this is probably our main contributions here, where we add the silicon level information. In addition to the silicon level information, we monitor aging, SCTs, SU power, supply, temperature, etc. We are also adding on-chip sensors to monitor operating system activity. We are now interested in two specific operating systems, Zephyr 3.7 and FreeRTOS, to monitor this scheduling algorithm, rate monotonic for these operating systems. And this is very interesting because the task priority changes during execution. So it's a real time task scheduling algorithms. The goal is to detect the faults that escape detection by the native fault detection mechanisms embedded in the kernel of the operating system in a mixed critical execution environment. What kind of faults can be detected? Faults can affect task scheduling process, violate task execution deadline, violate time and space allocated by the operating system for every task. So these faults are definitely targeted by our on-chip sensor that we call this specific watchdog. You find publication also on the literature. This is one of publication addressing this point. And the final goal here is find compliance, guarantee compliance with RINC 61 as RINC 653 standard, which specifies an operational environment for software application using the IMA, integrated modular avionics modules. So it allows simultaneous execution of programs with mixed degree of criticality on the same hardware platform. So this is very, very important from our understanding of point of view of silicon lifecycle management for critical applications. So almost the last slide that we have here, some example of validation that we have implemented. I have some case studies on different circuits, but I have separated only one for the talk of today. So that RISC SoC system on chip. This is the RISC-V processor that was manufactured. We are designing now the second version of the processor. The first one was finished the last year, so now we are taping out the second version of this processor, which is a highly reliable resilient quad-core multiprocessing system. That's why RISC tetra-core, and which has several multiple sensors embedded in for real-time measurement and system reliability management. So we have SEO monitoring, aging monitoring, temperature monitoring on that. And the system can automatically switch, depending on the information collected from the sensors, between normal operation, duplication and comparison of the cores, a triple modular redundancy of the core, 3 cores running the same application with a Volta, or quadri-cores running the same application with Volta. So we can switch them in real time, depending on the information collected for aging, for example, and guarantee a smooth aging of 4 cores at the same level, more or less at the same level, for example. So the chip is Skill for Edge, title, name of the chip, RISC-V processor, almost 45 square millimeters here. And almost the last slide here, we have a continuation of this example. So in addition to error detection and correction based extended hardening code, as everybody knows, a classic solution for error detection and correction in memory, as we can see the online approach running here. We have also added on-chip analytics to predict in-flight SRAM SU rate. This is based on AI training, artificial intelligence training, and hardware accelerator. So offline, we calculated the cross section of this memory, the memory used for the processor. It's the SSCD processor that presented in the previous slides, the theta risk. And based on the public historical space particle flux database GOES and ACE, we computed the software rate, and based on this information, we train a model, a neural network, artificial neural network. Once it's trained, we can configure the hardware accelerator with the network, and then we can perform S-run, SU, rate prediction of a couple of hours using this model. So, final considerations for this SOC. We discussed the high complexity of designing resilient systems for space applications. There is an endless number of parameters that can be combined in different degrees to induce to induce system failure. Temperature, conductor electromagnetic noise, ion power supply lines, battery induced power supply, fluctuation, aging, accumulated radiation TID, aging due to wear out, hot carrier injection, BTI, transient faults, electromigration, process variations, and so on. Workload, for example, is also very important, not indicated here, but workload plays a very important role in this case. IHP is tackling this complexity, designing space systems based on on-chip capability for lifecycle management. Such design is based on extensive cross-data information collected from silicon to operating system, or TOS, test scheduling algorithm, and then perform on-chip analytics based on this information. We have adopted the RISC-V as the instruction set architecture, preferred the instruction set architecture to implement these ideas. And this is also running with Zephyr 3.7 operating system, or the FreeOS version. And our chip have been designed and implemented with HP 130 nano by CMOS radiation-hardened technology, which this technology also is being evaluated for the European preferred parts list. And we hope that the project will be finished by next year. I think that's it. Moritz.
Yeah, thank you very much, Fabian, for this talk. Also, thanks for noticing that I basically switched on my video, but you were almost at the end already, so that's great. I just read 2 or 3 questions from the audience. So one is referring back to around your slide, when I remember correctly, slide 5. So Cirillo Maurizio asked, are these effects due to hot carrier injection? So I think it was basically around slide 5 where you basically mentioned, yeah, I guess so. So there was something going on, or slide 6 perhaps.
6.
Yeah, I just basically saw the time and not really controlled down the time. So basically,
anyway, can you repeat the question? I think the slide.
So the question was very simple. Are these effects, without specifying which effects, due to hot carrier injection?
Can
narrow it down.
Yeah, it can be bias temperature, stability, time-dependent electrical breakdown, hot carrier injection. Anyway, the idea is that we are monitoring the effect of this phenomenon, the electrical phenomenon. This means that we are monitoring aging, delay, increase. If you're monitoring delay, it can be, for example, electromigration. If electromigration increases delay, we are liable to detect with our own chip sensors. So we are covering hot carrier injection as well.
Yep. There was actually a second one which was being asked around your slide 9. Also not 100% specific here on my side. How effective is it to have on-chip temperature sensors? What are all effects this will be able to capture, and will it capture before the event becomes catastrophic? So basically the question is temperature sensors catching basically the events.
This is a very important question, and Intel is also very worried about that, because the processor was failed to be failed in the field at this moment exactly because of temperature. So they have hotspots, and so it's important to monitor when parts of the chip temperature increases beyond control, because at that moment you have to limit power supply, reduce clock frequency. Otherwise, you accelerate aging. So this is very critical. It's mandatory to detect these moments when you have temperature increase. And temperature increases depends on the application and how you are using your processor, for example. So it's very important to monitor temperature. This accelerates aging, reduces reliability.
Great. All right. So then also a question to you or a request to you, please go through the Q&A, all questions which were being asked and which we basically didn't phrase out loud now. Perhaps you can just answer in the chat. Then thanks a lot again to Dr. Vargas for giving this talk.
It was my pleasure.
We are switching, thank you so much. And we are switching over to the fourth talk in a row. Also a little advertisement to all participants. I know it's getting late in in some of your origins. Still stay alive here in our webinar, in our workshop. We still have 3 great talks coming up. The next one from Jakov Roisin from Tower Jazz, and then there are 2 more talks from ESA and NASA on the application side. So please stay awake and stay with us. Good. So the next speaker is Jakov Roisin. He's the chief scientist and fellow of Tower Semiconductor. He actually has been working for the company for the last 27 years, developing scaled-down CMOS technologies with embedded sensors and non-volatile memories. He actually received his PhD and habilitation degrees from leading academic institutions in the former USSR. And Dr. Roisin is the author of more than 350 publications, holds more than 80 patents, and he's also a full visiting professor at Technion in Tel Aviv University. So, Jakov, it's your stage. Thank you so much for being here.
Thank you very much. Do you hear me?
Perfect.
Yeah, okay. Thank you very much for inviting my talk, and thank you very much for making such a nice webinar. I'm going to download the slides. Just a moment. Here. Green. Share. Okay. Do you see my screen? Hello?
Yeah,
Yes.
Yes, I will move to the presentation mode. Just a moment.
Very good now. We see presentation mode.
Okay, I will put just the pointer. Okay, that's it. So thank you very much again. I'm going to report on the matrix radiation sensors in the floating gate version in the standard CMOS technology. So the outline of this presentation will be as follows. I will give a very brief introduction on Tower Semiconductor. It's the new name of Tower Jazz, maybe an old one, but now we are Tower Semiconductor. I will speak about the radiation sensing based on floating gate principle with a little bit history. Then we'll report on C sensors, single poly floating gate devices that allow testing both high and very low radiation doses. Then I will speak about the version of C sensor design, which is a matrix radiation sensor. We call it Jupiter vehicle. And then about the data processing to reduce the influence of noisy pixels in the floating gate arrays, and how to mitigate the effects of degradation. And I will give some examples of response to radiation, to X-ray and alpha particles, and a summary. So starting with the company, Tower Semiconductor is the largest analog CMOS foundry. After the large digital foundries like TSMC, UMC, Global, We are the largest company with annual revenues of approximately $1.1 billion, and we run fabs all over the world, 2 fabs in Israel, 3 fabs in the United States, 1 in Italy, and it is shared with ST Microelectronics, and 2 in Japan. So besides that, there are multiple offices in the world for sales, for marketing. The technologies that we run in these fabs range from 6-inch 0.35 micrometer to 45 nanometer on 300 millimeter wafers. And the products that are fabricated by our customers are very different. Sensors, different types of sensors, image sensors, non-imaging sensors, including radiation sensors. We have products connected with RF applications, RF SOI, power management by CMOS, processes CG in different fabs. And these fabs have fab cross qualification. It means that the same technology is run in several fabs in order to allow customers to allow actually to use their needs to be able to fabricate in different locations. Okay, so now about the ionizing radiation sensing based on floating gates. So it's very well known that a floating gate transistor, a memory cell, floating gate memory cell, can be used as a radiation sensing device. This was actually reported for the first time by Dov Froman-Benchkovsky, who invented EEPROM more than 50 years ago. They erased the EEPROMs by X-rays. The principle is rather simple. So the floating gate is charged, in this case with electrons, as it is shown in this drawing. The control gate of the device is made large. So usually we try to make a thick dielectric and a large area control gate. This acts as an ionization chamber where actually the interaction with radiation happens. If we measure the IV of such a cell, of the programmed cell, it will look like this. There will be IV characteristics of the programmed cell. And if it is subjected to radiation, when there is a particle passing through the control gate, or a photon, and there is a track that leaves electron hole pairs. These electron hole pairs will be separated, the floating gate will be discharged, and there will be a shift of the IV characteristics of the transistor. And if we put some reference voltage, by the difference in the currents, we can estimate the radiation dose absorbed by this device. So regular studies of such devices also are known for a long time. They were started in Sandia. Then the use of large floating gates on field oxide to increase sensitivity to make the ionization chamber larger were reported by TAR for Carleton University. There were numerous designs, papers, and patents to increase sensitivity, decrease operation voltages, to decrease power consumptions, to compensate for reliability issues, thermal shifts, retention issues. Arrays of such sensors were implemented using standard floating gate memory cells for imaging of radiation. We also contributed in this field by designing single polysilicon floating gate C sensors. This is our design, and arrays of such sensors. The distinguishing feature of these sensors, I will speak about this a little bit later on, is the use of high quality oxides and voltage sharing between isolated P wells, and this allowed us to make very low, ultra low power consuming memory cells that acted as radiation sensors, C sensors. Their prototype was called C-Flash. We run this technology in our numerous fabs as a memory for our customers. And what I'm going to speak about is a version of these memory cells specially designed for sensing radiation. I will speak about these sensors, and I will speak about the arrays of these sensors, which actually have an advantage because they allow not only measure the shift of the IV characteristics, but also to count the number of pixels in this array affected by radiation. This allows to make very sensitive cells. But at the beginning, I would like to report on the C sensor, what is the distinguishing feature of this device, and what is common with other solutions using floating gate radiation sensor. So you see the cross-section of the device in the drawing. So the distinguishing feature is that the ionization chamber, which is STI, large STI, in the top view, it's a large area in the layout that you see on the right side, is in the isolated P well. The floating gate is common for this isolated P well and another isolated P well, which acts as a tunneling capacitor. And there are coupled to the same floating gate transistors that act as readout transistors. In different designs, we use or their combination or one of them. So what happens? We charge the large floating gate, it is subjected to radiation, and then it is measured again. So the common features with other radiation sensors based on floating gate principle is that charging of the floating gate is done by Fowler-Norgam injection, and this allows currents in the nanoampere range for charging, low power consuming. It does not require any external voltages during exposure to radiation. So it can be operated without being not connected to the voltage sources when testing radiation. And it allowed, because it's a kind of integration of radiation, it allows measurements of radiation from sources with very low dose rates. This is common for this design, but distinguishing features that we have is that we implemented this type of sensors on high quality STI in the technology with very low trapping in spacers, in the technology where the isolated P well has low doping. All this allows to form a kind of a radiation-hard core CMOS process flow flavor. And thus, such devices remain stable. They remain stable sensitivity up to rather high radiation doses. We verified it up to 100 kilorad. Probably it's possible to have no changes in sensitivity to higher doses. The second distinguishing feature, the voltages for operation are divided between the isolated P wells. So it allows, first of all, to avoid high voltage devices, special high voltage devices in drivers of the circuits, and it allows easy addressing in the arrays. Also, we use a separate tunneling gate, and thus we have immunity of readout transistor to gate oxide stresses. So transistors are not stressed in operation when we repeatedly program the floating gate in order to measure large doses. And also all this design has a relatively small footprint. You see the dimensions here. This 12 microns by 17 microns. This is a single floating gate. Out of these devices, we built an array. So the next slide shows C sensor arrays. The operation principle of this array is comparison. We measure VT difference of the defined pairs of sensors. One of them is sensor and the other is reference. This reference can be or a transistor or a radiation insensitive device, which is C-flash, an analog of C-sensor, but not sensitive to radiation. But it can also be the same C-sensor. In the first situation, when it is a constant reference, a reference not insensitive to radiation, we use the array for measurements of high doses. So we compare the sensors in the array with insensitive dummy pixels. Then we measure the differences of VTs under radiation. We plot the distribution of the response of these sensors to radiation. And then we calibrate the position of the maximum of this distribution by using some standard radiation sensors. The other mode of operation, which is used for measurements of very small doses, and this is the what we want to distinguish in this technology, is making two identical sensor arrays. They may be physically sensitive. They can be sensitive by definition of the position of the pixels, but the sensor in one array has his partner far away from in the other array, so that the same photon or the same particle does not influence both guys together. And we measure the difference of the VTs of these two sensors. Then we calculate the number of influenced pairs of these pixels, and this is an indication of the absorbed dose for low doses. In this way, we are able to count single gamma quanta and to count single alpha particles, for example. I will give examples of this registration. And we have special reading algorithms, of course, because such a technique that is based on measurements of very small variations in the VTs. We have some techniques to exclude the influence of VT spread, noisy pixel, retention effects. I will speak a bit about it later on. So how did we implement this technology? We built what we call Jupiter test vehicle. This Jupiter test vehicle is actually a silicon chip comprising C sensors and allowing for our customers. We are a foundry, we don't have our products. It's simply a vehicle, though some customers use it as a product, but it's a vehicle. Others customers can use it for development of fully integrated radiation dosimeter products based on this principle. The characterization vehicle, Jupiter, is a 64 kilobit C-sensor array, 250-60 by 250-60 rows and columns. The die size is approximately 7 by 7 millimeters. It is shown here. These are the voltage supplies. Rather small power consumption. The process is 5-volt CMOS for 4 metal levels. Readout is from PMOS in this case, because in the charged states, all the pixels are in the state of accumulation and the surface traps are filled with holes. So for reading, the cells are brought from this accumulation state into the state of readout when the IV characteristic is measured, and this way we are able to suppress 1/f noise. The device has internal column parallel 14-bit ADC, and it has C-flash as references, or C-sensors are the references themselves. The product is placed in the packages without a lid, with removable lid, so you can irradiate it through the lid or without lid. And we have a board which was designed specially for running these sensors. and it has a friendly interface, user-friendly interface, in order to make radiation measurements. And below you see simply a result, what will happen with this matrix under irradiation. Just for illustration, you see blue and red dots. It depends in the pairs which of them was hit by alpha particles and whose VT decreased, or in the pair the difference increased. So this is Jupiter. So how this procedure is done? The procedure is measurements is done in the following way. As I said, in the large dose detection mode, we compare rows of the product. These are the rows of the product of this Jupiter. We have a dummy row that has insensitive sensors. So we compare each of the rows with the dummy row. And in this way, we can plot the distribution of VTs of all the pixels in the array. The spread of this distribution may be between 100 and 300 millivolts, but the shift of the distribution under radiation when pixels are discharged is in the range of 110 millivolts. So we can reliably test 1 millivolt shifts. And this allows us measurements with rather good accuracy, even in this mode, which we call large dose detection mode. We are able to measure at the level of 1 milligray, 1 rad, 0.1 rad. So something at the range of doses that are able to be measured reliably are at the level of 1 milligray. So in the case of small dose detection mode, we are able to go even to the level of single events, single photons that impinge the matrix. Just for information, for example, in order to detect 10 microgray, it is necessary to detect 1 mega electron volt photons per 1 millimeter of sensing surface. So we need to count photons for it. To count photons is rather complicated. What we do, we compare the rows in one array with the rows in another array. In this case, we compare C sensor to C sensors. We plot the distribution of the difference of these sensors, and we look at the distribution without radiation and with radiation. We look at how this distribution is widened. And this is the measure of low doses in our case. Later on, you will see in practice how it works. As I said, it's necessary in order to be able to measure such small doses as we are targeting, it's necessary to make some tricks. First of all, we are making data processing to reduce the influence of noisy pixel. How do we do it? We measure for a certain time VTs of all the cells in the array. And we look at the width of the distribution, of the VT distribution for all these cells. Out of all these cells, we select, we map what we call the quiet pixels, good, which are having lower noise, because some of the pixels have random telegraph system noise and maybe other noise mechanisms. So we are able to select only the pixels which are supposed good. For example, here in the drawing below, you see the lead operation that was performed multiple times, 100 times in this example, and only quiet pixels were selected out of the whole distribution for the further analysis of small dots. So at the picture on the right, you see the blue background. On the blue background, you see light dots. These are the good pixels. These are the good pixels which were taken for further radiation measurements. Okay, this is one trick we do. And the other trick is reduction of the influence of the retention effects. In any kind of non-volatile memories, and this is a type of non-volatile memory that we are working with, there is a certain retention. Our memory is perfect, one of the best. It has very low retention, very good retention, very small charge loss in the memory cells. As I said, it's one of the, actually all this technology, radiation sensing technology, was built on high quality non-volatile memory that we offer to our numerous customers. But even for premium quality floating gate NVM, some cells slowly lose their charge. And if we want to make such extreme measurements at the level of single photons, we need to make some kind of a correction. So on average, the charge loss in our memory arrays is uniform. No tails in VT distributions. However, when we compare cell to cell, there are variations in the small dose registration modes. So this fluctuation in charge, they can widen the distribution of VTs of the initial arrays. So in order to compensate for it, what we do, we use special algorithms. So we look at the distribution of the memory cell without and with exposure. And actually we make compensation. We mitigate the influence of retention effect. We make a comparison of the cells which are not subjected to radiation, the cells which are subjected to radiations. So we make comparison of the affected cell and the non-affected cell, and so thus we can exclude the effects of random changes in the floating gate charge of this memory cell. So this is the second trick that is employed in our products. And now I'm going to give an example of how the product, how this Jupyter test chip, it's actually not a product, it's a prototype of the product, but some customers use it as a product. How it is, for example, response to the X-rays, one of the radiation that was tested on these Jupyter prototypes. There are two detection modes, large detection modes and small single event detection modes in this case. In the large detection modes, we are looking simply on the decrease of the VT of our memory cell as a function of the exposure times. So we see that there is a linear shift of the VT, and the distribution at the peak of the VT distribution moves proportionally to the absorbed dose. In small dose detection mode, what we see that the standard deviation of VT distribution increases, and this is the measure of the absorbed dose. So here in the left bottom picture, you see how the VT shift is measured after 1 milligray dose. Actually, VT shift of 30 dN in our case, corresponding to 7.5 millivolt, corresponds to 12 milligray. So we are able to have 1 milligray dose resolution. In this case, we are not counting single photons. It's the shift of the VT distribution. Another mode of operation, what is shown on the right, is looking how the distribution of the VTs changes as a result of radiation. So actually here on the right, we are testing the single effects in the interaction of X-ray photon with our matrix radiation sensor. So 1 dN here corresponds to 0.25 millivolt of the change in the VT of the programmed floating gate of our memory. So we are able in this way to get to approximately 50 microgray resolution. And this is shown on the graph below, where you see the standard deviation of our pixels in the array without and with radiation. So for the exposure time of 10 seconds, we are able to test about 50 microgray of radiation. So this is the test vehicle that we used for testing the technology, but similar results were obtained by several tower customers which were using Jupyter vehicle for their applications, both for gamma and X-ray radiation. So most of these customers reported that doses below 100 microgray were shown feasible with this technology very reliably. So the next slide, and actually this is the last slide showing this technology, is the response of Jupyter vehicle that I spoke about to alpha particles. In this case, these are the alpha particles from americium source, 5 mega electron volt. So this is the distribution of the bit count, and this is the changes of the threshold voltage of the memory array. Each one, the N is here 0.25 millivolts. So we could reliably measure very small fluxes of alpha particles. And actually for 10 seconds with our sources that we use, this is a americium source that was used in these experiments, 20% of all pixels in the array were hit, and we could reliably detect these effects of single particles. So this is what actually I wanted to report. So in summary, a novel principle of radiation measurements using matrix floating gate sensor was suggested and verified using Jupyter, what we call Jupyter test vehicle. The technology was implemented on the radiation-hardened 0.18 CMOS production platform without additional masks. We have similar results also for 65 nanometer CMOS platform. The developed measurement algorithm allowed to decrease the effects of noisy pixel. We could select those pixels that were suitable for this technology, and to account for floating gate charge retention effects. So we received record resolution of less than 50 microgray for X-rays for floating gate sensors. This was done by counting the affected by radiation pixels in the mode that I explained when we are not measuring the mean VT shift of the memory, but count the number of pixels affected by radiation. Thank you very much.
Thank you very much, Jakov, for this excellent talk. There are actually a couple of questions, and I just started reading them aloud. One was, I don't know if you can say that, the question was already being asked before, but perhaps you can also answer that one. For photodetectors, which one is more destructive, TID or SEE? So basically total ionic dose or single event, single events. So that was actually a question which
okay, the same sensors allow actually both modes. They can be used when the array is, when the pixels in the array are referred for to the register of the cells that are not affected by radiation. This is the mode of large dose in our case. And we have the mode, the second mode, when we compare two arrays, each of the sensors of these arrays is the sensor. we measure only the difference of the VTs in this sensor, compare this sensor. This is the mode when we can test single effects. In this case, we can count the number of pixels that were affected in the array by radiation. So the same array, the same product allows two modes, one for large doses and one for extremely small doses.
Good. Then there was a second one, which I also read aloud. How do we check the multi-threshold voltage cell reliability towards radiation in a single chip? And how do we separate the power blocks?
Okay, so actually this technology that we developed is based on radiation-hardened platform. So we make experiments at different doses, at different dose rates. And so compared with other similar technologies, we have very low degradation. This is connected with a special STI that we use in our products and the special back-end dielectrics. So it still has some degradation, but as I said, up to 100 kilorad, we practically do not see degradation of our pixels. So for larger doses, we have to take care of the degradation effects. But once again, we are not making sensors, we are proposing technology. If the customer wants for higher doses, we make some tricks. And for lower doses, and this presentation was actually mostly focused on our ability to measure low doses, we don't see degradation effects.
All right. Perhaps one last one. Richard Smola is asking what influence of temperature, and is there a compensation against temperature variation?
All this technology is with the same reference. For example, in the case of large dose measurements, the reference is the same cell with the same design, but it only has a different design of the ionization chamber, but the transistors and so on are the same. So their response to temperature are the same. So one refer to the other. In the case of low dose, critically low dose, we compare apples to apples. These are the same in the reference array. In the measurement array, we don't have reference and measurement array. They're identical arrays. We measure the difference of the cells in the identical arrays.
Good. There was a last one just coming in. I also read that one aloud from Alok Das. Is it possible to test in SPICE simulators, or is it possible to test by a MATLAB kind of simulator, like a multi-physics simulator? And then as a follow-up, what method did you follow to test the circuit before manufacturing?
Yes, it's possible. So we have different options of measurement. As I said, we have testers, which are a chip. They're packaged in a standard package, and they're placed on the board. The board can have an extension cable, so you could put it in the radiation environment. You can move it into space, and so it was designed. All the system was designed to show the customers how they can use on practice this technology, and some customers already do it.
Very good. Okay, then thank you again very much, Yakov. Excellent talk, and we would switch over to Philip Neudig.
Thank you very much.
Yeah, thank you, Jakub. So Philip could take over the screen if he likes to. And perhaps I take the moment of silence to already introduce him. So Dr. Neudig actually received his Bachelor of Science, Master of Science, and PhD degrees in electrical engineering from Purdue University, West Lafayette in Indiana, USA, in 1986, 87, and 91, respectively. In 91, he became the lead semiconductor device engineer for silicon carbide sensors and electronics research team at NASA Lewis Research Center, which was later renamed to the NASA Glenn Research Center. He has overseen the design, modeling, fabrication, and electrical characterization of many prototypes of silicon carbide electronic devices, especially being developed for high temperature, high power operation in aerospace-related systems. Dr. Neudig is presently focusing on the development of increasingly capable silicon carbide extreme environment, durable integrated circuit electronics technologies. He's a fellow of the IEEE and was honored by several awards and we are very much looking forward to have him here as a speaker. Philip, your stage.
Hey, thanks. Can everybody hear me and see my screen first?
Yes, perfect.
Okay, great. So yes, on behalf of our group here at NASA Glenn, we're going to switch gears here from far more mature technologies that we've been hearing about today to very much an emerging and immature technology, but it's one that has some unique properties that I think will help benefit systems. And first of all, I'm going to point out that most of the work you're seeing here was done by a team at NASA Glenn. I'm just sort of the talking head to the subject. And we've been developing our technology for high temperature applications, but there's certainly potential in it for high radiation. So I'm going to basically touch on both subjects and of course, try to get this technology from its infancy into accessibility and use into applications. So NASA's been developing this technology to basically benefit high temperature electronics missions. Primarily our funding here at NASA Glenn has come from intelligent propulsion systems, where we want to put electronics basically in very hot areas of jet engines or other areas that are very hot in an aerospace system. And more recently, our funding has actually been coming from Venus exploration because the ability to operate electronics, integrated circuit electronics at very high temperatures without shielding or sheltering, basically could fundamentally enable a whole new Venus lander mission and really open up that planet, which geologically is much more similar to Earth than Mars, to exploration. Now, in terms of high temperature, which will be the first part of this talk, I mean, high temperature devices have been around for a long time. And actually, over 30 years, people have been demonstrating using wide bandgap semiconductors and actually even in silicon and insulator prototype device results that function, briefly for, at temperatures above 450 degrees C. All right, there's lots, if you look in the literature for over 30 years, there's lots of papers in this area. But what's missing from all of these reports is the ability to operate a device for a long time at 450 degrees C or higher. And that's really what we targeted our development here at NASA Glenn, was to basically, this is not a mission deployable technology until it has become stable for many, many, hours, years of operation. And so that's really what we have focused on, is trying to get this technology so that you can actually deploy unsheltered electronics in very high temperature areas. And so from the start, being durability is our main criteria, not necessarily frequency, performance, or other metrics, circuit metrics. We decided to develop epitaxial N-channel silicon carbide JFETs. We figured basically let's at least establish a foothold in a very durable technology, and then we can begin to bring capabilities to bear where they're needed for these applications. And of course, silicon carbide is a wide bandgap semiconductor. It's well known, operable at very high temperatures, but it's also very stable. If you're looking for durability, this is a material where reactivity is very low. Dopant diffusion is negligible at the temperatures of operations that we're going to be operating at. And of course, we chose a JFET because it's a majority carrier device. And you can use epitaxial junctions. They're the lowest leakage, highest quality junctions. So your leakage to your transistor, your parasitic leakages for signals are going to be at their lowest. And of course, the N-channel JFET basically has minimal sensitivity to a P-type contact to the gate. Most of the current's flowing through the N-type contacts. Now, you'll look out there in the literature, and there's other transistor types that are, out there, and they have better performance metrics in terms of frequency and power and things of that nature. But again, these are technologies that are very inherently tougher to render stable for high temperature. And again, that was our primary application, going into this is high temperature. In bipolar transistors, you have minority carrier sensitivity, and you need a good P-type contact to make that device viable. For MOSFETs, CMOS, of course, MOS junction sensitivity, we've heard some of that today. And with respect to radiation, it's also true with respect to temperature. MESFETs, basically the gate junctions are too leaky for the kinds of temperatures we're looking at. And of course, 3-nitride HFETs, certainly are a candidate for some of these applications someday, but they of course have sensitivity to their heterojunctions, and the material is less inherently inert and more reactive than silicon carbide at high temperatures. And of course, using this approach, over 10 years ago, we demonstrated very stable transistor operation out of this device. And you can see here the very little change in the IV characteristics with this device operated for 10,000 hours. And one thing I will point out is this 10,000 hours is actually in air. We are not relying on any hermetic packaging at all. This device is actually exposed to air. And you can see you get very stable results out of it. All right, so the circuit approach that we have put together with this, and of course the technology's evolved since we've been doing the discrete devices, is basically based, we call it a JFET-R. And you can see the core device is a junction field effect transistor and a resistor. And both of those are made out of the same N-channel epi layer, of course. And so the advantage of that is that guarantees that your inverting amplifier, which is of course a baseline circuit, the temperature dependence is the same. The resistor doping goes, the resistor resistance goes up with temperature at the same time as the transconductance of the JFETs goes down. So they basically cancel each other out, and it basically enables built-in temperature dependence for this technology. I'll show an example of that in another slide here. We operate our designs based on layout ratio-based circuit design. We don't use absolute component values. We just say this many squares, because the temperature ranges we're talking about, the transistor, transconductance, the resistances, they change by over a factor of 4. And so again, we've designed this technology to be a broad temperature range technology, and this is how it works. We are using depletion mode normally on devices. Our threshold voltages are non-zero, and you have to apply negative voltage. So we actually work in negative logic space, if you will, negative signal space. And our voltages at this point are -1 to -10 volts is what we've been demonstrating. And of course, we need a VDD and a VSS power supply. Now we bias the backside here with metal contact. We bias the substrate bias at -25 volts. Again, you want to prevent, for these high temperatures, you want to prevent signal leakage, leakage of your signal, if you will. You want to keep all junctions either at 0 bias or reverse bias. We don't operate any of these transistors at forward bias. And so this is schematic diagram here on the right is just what our basic digital logic gate, which is nothing more than the logic element itself, and then a level shifter to get it ready for the next stage. And so as far as the temperature performance goes, here you can see a comparison of a 6H transistor. And of course, we initially were developing in 6H. We're now doing 4H technology because that's where the commercial manufacturing of silicon carbide for room temperature devices has gone, as 4H. But you can see here big difference in the JFET characteristics, but with that resistance also going up, you actually get an inverting amplifier that shows very, very little change in its gain properties from 25C all the way to 500 degrees C. And of course, this works both at low temperature and at high temperature. And here I'm basically showing one of our tests that we did with a prototype logic gate some years ago. And basically it's showing operation here from -190C all the way up to 812C. And again, just using this, the built-in temperature compensation of both the device and the circuit technology that my colleague Mike Krasowski developed. And so you can see here, here's the plot of versus all the temperature range, and you can see there's absolutely no changes in the power supply voltages and no changes in the signal voltages that are going in. And of course, this is really important, having this thing, because we can pretty much tell if our circuits are going to work up at high temperature, just based on yield screening at 25 degrees C. And of course, cold start capabilities are really important for some of these aeronautics and aerospace applications that we're trying to develop. So again, this kind of functionality would cover the entire operating range for a commercial aircraft, operating in a turbine engine environment. Okay, now the technology, of course, it's not just the transistor, it's also the interconnects. And so a lot of our time was spent in this technology developing a 2 levels interconnect that was basically almost as stable as our transistors. And these are based on tantalum silicide interconnects. And you can see we're not using exotic materials here. We're using things that are available in the silicon industry, which is SiO2, silicon nitride. And so we've basically tried to make this technology compatible with silicon manufacturing techniques. So this is basically a fib cross section of one of our basic JFET devices. Now, there's a lot of tricks and a lot of work that went into this. And I basically put it in bullets, the three major processing things that we've, down selected over the years. And again, we are over designing these devices and over designing this technology so that it will last for a long time at 500 degrees C in air. And one of the things is, of course, we're using close proximity sputtering of tantalum silicide, very close distance, so we get conformal coverage over this. We're using LPCVD TIOS for depositing, our silicon dioxide, and we're also using LPCVD to do silicon nitride. And of course, the interconnect is well protected beneath all this dielectric. To be able to run circuits at high temperature, of course, you need packaging as well. And of course, we've in parallel developed those technologies. One of the key technologies for us is to get the signal off of the chip out of the passivation, which is an iris bond pad metal stack. And of course, this was developed by my colleague, David Spry here at NASA Glenn. And of course, packaging, multi-chips, this has also been developed as we've been working on the semiconductor technology, is you have to obviously go to a ceramic-based technology. And we're up to the point where we're building modestly complex boards and packaging those chips successfully on them. So here's basically the result, what I call our best durability result to date, which is an IC generation 10. And of course, it's, as you can imagine, it takes multiple generations of learn by doing to actually get this far. And in this one is just basically a simple, RAM chip. It's just a simple 4x4, it's 16 bits. Large size. We're not doing any submicron features at all in this technology at this point. These are 6-micron gate length devices. Again, just trying to demonstrate that we can durably do something, in this environment. And as you can see here, this test is actually ran for 421 days, 500 degrees C in air. And again, the device was not hermetically sealed at all from the air. It was exposed to the room air ambient. And basically the device worked perfectly for that time. And here's sort of the plots of this versus temperature. You can see here's the temperature independence that I talked about. The output signal levels change very little as a function of temperature. And of course, here's the output signal levels as a function of the test time. Over a year at 500 degrees C, you can see it's very stable. There's a little bit of burn-in effect in the early stages, but after that, everything gets very, very stable. And of course, this is what you need if you want to do longer term missions in some of these aerospace environments. Now, as I mentioned earlier, Venus has been one of our primary funders more recently, because that is such an unexplored member of the solar system. And so at NASA Glenn, they've actually built a Venus environment simulation chamber, and it is a beast. But of course, Venus is this incredibly hard place to explore. It's 460 C, it's 92 times the pressure of Earth's atmosphere, and on top of that is a very reactive chemistry. And so there's a chamber that was built at NASA Glenn for studying all kinds of things for future Venus exploration missions. And we threw our chips into this chamber, and again, we tested them with no lid on the package, basically as you see here in this photograph here. And of course, these are very simple chips. They're only they're less than 200 JFETs per chip. But you can see here over the entire 60-day test that the operation was extremely stable throughout the operation. And so this chip functioned. It did what it was supposed to do after 60 days, and then cooled it back down. And so this really is a potential game changer for landers on Venus. And for those of you that aren't familiar with Venus, basically in all Venus missions in the past, none have lasted more than 2.5 hours. Okay, the approach was, and the Russians did some marvelous work, many decades ago, of landing basically great big pressurized spheres on the on the surface of Venus, and they grabbed all the data they could within a couple hours, and then the mission was over. And of course, you compare that to like the rovers on Mars, they're running for years and returning years of science data. And so that's one of the reasons Venus is just much harder to learn from what's going on the surface, because of the electronics. So anyway, NASA's thought about many times doing, big heavy landers, and this is just one of those things. If you have to use sheltered electronics, you still end up with this huge, 686 kilogram sphere, and you still only get like 5 hours of surface mission. But if you design a totally new mission concept based upon the unsheltered silicon carbide electronics, you can do a 60-day mission, and you can do it for less than 20 kilograms. And of course, this basically just is like a weather and seismic station. It wakes up periodically, sends data, and then goes back to sleep. Most of this mass, by the way, is battery mass. So that's what you're after when you develop a new technology and you invest in a new technology, is trying to unlock that potential. So now let's move on to the high radiation environment potential. And again, it's potential. It's yet to be proven. And of course, the same trade-offs, similar trade-offs, not the same, apply for high radiation missions. And I'm just showing a picture here of the Juno spacecraft as it was being prepared for launch. And of course, that mission is flown. And you look at this, and all the electronics for the mission is sitting in this vault. It's a 180 kilogram vault, and it's comprised of 1 centimeter thick titanium walls. Okay, so that's 180 kilograms just to run the electronics for this mission. And of course, they obviously did things at the mission level, this is of course going to Jupiter, which is a very high radiation environment. They of course, optimize the mission trajectories and whatnot to minimize the exposure to the radiation belt. So, the whole mission is an engineering trade-off. And of course, eventually, the icy moons of both Jupiter and Saturn are both candidate places for possible trying to find life, or at least the seeds of life in some of these potentially places where there's liquid water. And the prior mission concepts without silicon carbide electronics, you have to have this big heavy vault to hold your electronics, and that really precludes mobility. That precludes you from being able to go places, go after the geysers or vents or places of interest. You're really stuck in one place. And so again, the possibility of running unsheltered electronics really makes a big difference into your science return possible in a future mission. So we took some of our high temperature JFETs and the simple integrated circuits like I was showing you earlier, bring oscillators and flip-flops and things of that. And we were, with the help of our colleagues at NASA, NASA Goddard, went and did some radiation testing. And we actually only had the budget and resources to go to 7 megarad. And of course, nothing failed at 7 megarad in these junction devices. As you heard about in the earlier physics, you would think that a JFET's very rad hard. And of course, silicon carbide is rad hard itself. And so we went to 7 megarads, really saw no failures. We also tested against heavy ions all the way up to the gold standard. We saw no destructive effects happen. Of course, these are lower voltage devices. I know in the literature for high power devices, of course, there are some destructive effects to the heavy ions, but for signal level integrated circuits, we saw absolutely nothing in terms of that. We did see some single event upsets. I will say though, in our regenerative circuits, like our flip-flops, there was absolutely no single event upset in any of those circuits. It was really where we only had, open nodes sitting in a circuit that we would see glitches, software SEUs. And of course, if you look in the literature, silicon carbide against the various radiation, there's certainly things that give us hope that when we actually do get to test these integrated circuits that we're developing to higher levels of radiation, that things will work out very well. Again, this is work from, on the left here, from 30 years ago by the Army Research Laboratory. And you can see that they're getting to quite high neutron fluences, and this is all irradiated at room temperature. There's, of course, annealing, effects that can happen if you're operating at high temperature and high radiation. But still, this is a pretty good fluence to get to. And of course, there's also been testing against TID of silicon carbide JFETs. And again, this is a group over at the University of Hiroshima. They're going all the way to 900 megarad, and basically their devices, their silicon carbide JFET technology is still functioning in this regard. Okay, so we have this technology in its infancy, and we're trying to push to get people accessibility to it, and so that circuit designers like yourselves can actually make use of this technology if you have an application that some place to go that you don't want to haul around cooling or sheltering to do. And so we actually have posted an online design guide here. We actually have two of our generations, generation 12 and generation 13. And we've put the technology out there to have a multi-user approach. We are doing some external partner designs in the Gen 12 fabrication run, which we're hoping to finish up in the near future. Those are available through Space Act agreements with NASA. But we really are pushing towards, commercialization of this technology. And certainly one of the companies we've been working with is Ozark IC. There's commercial design services available through them. And we're also starting a collaborative project to improve, design kits and manufacturing access as we speak. So if you want to kick the tires of this technology, you can find what I would call rudimentary SPICE models to try out and see what circuits you could design that might benefit you using, from the information on this webpage. And so this sort of just shows the growth of our technology as it's been happening in the more recent generations. Of course, I showed you the IC Generation 10 result already. Generation 11 was a more complicated one. Unfortunately, we made some changes to our interconnect process that were not entirely successful. So this was actually not a 500 C durable technology. We hope to have these fixed in our Generation 12 that's coming up. And so again, RAM is a benchmark of upscaling the technology. And you'll also see it's very important is we're trying to get this technology into a foundry. And so we are working with GE Aerospace to start processing parts of our process here. We're still on both Generation 10, 12 and 13. Some of the processing is done at NASA Glenn, but a lot of the processing is now starting to be done at GE Aerospace. And of course, eventually that tech transfer would be hopefully complete so that people would have access to the technology through GE Aerospace or any other commercial foundry. It doesn't have to be GE Aerospace. They've just been the first partner who's stepped up and we've worked with in this regard. And just to show you where we're at right now is, we have 50 different application-specific circuit ICs. We actually have a microprocessor dual chip. We actually couldn't fit it in one chip with the technology, but it's actually 2 chips. We're doing both mixed, digital and analog. We're doing ROM and RAM. Certainly a missing piece of our technology is, if you will, a programmable ROM. It's kind of tough to do something that lasts at 500 C for a long time and have a storage element that fits that bill, but that's also an active project that is under development. We're also obviously demonstrating the circuits that it's going to take to make that Venus lander I showed you earlier. And we've been working on all the sensors for that as well. And of course, you need some power, a little bit of power JFET chips. These don't have to be kV devices. These are merely like 50-volt devices. But these are also being run in the same process as our integrated circuits. And of course, we do have some Space Act agreements. And of course, there's the model is of course, sometimes NASA works with the partner to design the chip. Other times the chip is completely laid out and sent to NASA, and then we implement it, using our logic. And this is just a picture of our tech demo board, that we're working on. We're hoping to build this board once the IC Generation 12 chips come out of the fab, and then test it in Venus environments, and hopefully also be able to test in large, in high radiation environments. And one of the points I do want to point out is we have all of these complicated radiation hard processes, right, and high whatnot. But if you need to go somewhere, simple ICs that are of the complexity that we're already starting to demonstrate actually have successfully explored the solar system. Voyager is considered one of the most beneficial missions of all time. We still see it in the news every now and then. They're still pinging Voyager out there in interstellar space. I mean, it was built using, chips of this technology. And so, at this point, if you need to do something in a harsh environment, get a signal out to, if you will, the more complicated, more benign environments. This technology, we're really hoping that it's going to be able to come online and be accessible soon. We're working hard for that. And just want to give you a summary perspective here as I'm wrapping up. For infusion into most applications, you really need a stable IC system. You can do those. There's ways, we've heard certainly in earlier talks, there's ways to get to a stable IC system even when your devices may be changing a little bit due to radiation. But the user has to know that his part is going to work for it to find its way into missions. And so far, the results I've shown you, NASA Glenn is the only place that can show you these kinds of results. Nobody else has demonstrated, 1-year operation at 500 C. And we really are interested in finding out what's the radiation tolerance, of our actual technology. Again, I'm an experimentalist. Theoretically, it should be good, but I'd much rather have actual data to show you, and we're working towards that end. Now, also, of course, we've seen other conventional more conventional temperatures, less durable IC technologies are very viable. All right. People are always often coming to us and saying, well, how about using silicon carbide? I'm like, well, you've got other, more developed options for your environment. Your environment's just not quite harsh enough that you need silicon carbide yet. So, obviously we're all engineers. We all want to take the path that makes the most engineering sense to meet something. But hopefully with some technology improvement, upscaling, and access to foundry design and manufacturing, we can open up this basically 500°C environment and TBD radiation environment for, applications for people to use. And again, we can go to low temperature as well. And so, I sort of call this a go anywhere, IC technology in its infancy. And hopefully we can, continue to make progress on this. And with that, I will close up and take questions.
Perfect. Thank you, Philip, for this wonderful talk. So I'm just reading out one question which came up during your talk. Sang Dong wrote into the chat, not knowing all the details, but why is doping diamond difficult? Can we just not use ion implantation of impurities as other doping methods? Do you have a comment on that?
No, because I'm not really a diamond person. I know that I can do the doping that I need to do in silicon carbide, and have had it available to me for decades. And I will defer that question to someone who's an expert in diamond technology.
Okay, very good. So I got actually one myself, which is like you have just shown on your last slides what you can now all do in this silicon carbide technology, which is very impressive. Are there things which you still can't do in it? So basically, like when you're now planning a mission as you do, will you be able to support basically all the electronic needs with the silicon carbide chips, or are there different things which you basically still need to, use different technologies, different semiconductor material for?
So you always, I should say, you always need more capability, right? And I sort of touched on it. I mean, we have not successfully developed an NVRAM technology yet for the silicon carbide, for instance. Okay, so that's a pretty important component of most robotic spacecraft. And again, the robotic Venus landers that I was showing you, those are very, very simple missions, if you will. And the ability to, they're basically based on the ability to transmit only and not necessarily receive and reprogram, right? But things are much better when you can receive and reprogram, as we've seen in recent news events when, when rovers and things, have glitches, if you will. So yeah, there's a lot more to do. But again, we want to get to a place where we at least demonstrate an initial mission with some initial viability and initial science return that was not possible before.
Yeah.
And so, yeah, it's one thing at a time. And certainly non-volatile RAM is one of the important things. Higher frequency operation is also something. I mean, we built our JFET technology mostly on lower frequency stuff. And we're obviously trying to push to higher frequency to be able to do, more viably do, data transmission, if you will. That happens at the higher frequencies.
That was exactly basically my follow-up question, and there has just basically been one question in the chat by Murty. What is the RF performance of silicon carbide FETs at elevated temperatures? So basically, can you do the RF transmission?
Yeah, and the answer is the JFET actually cannot, and so we're pushing in. It's public knowledge that we're pushing also to do more of to try a bipolar transistor and try to stabilize that, make that a high temperature durable, transistor for doing an RF transmitter. So yes, that's for doing the more viable frequencies, which would be above 100 megahertz, if you will. And the JFETs, the 6 micron gate lengths, yeah, you're not going to get very high frequency. It's going to be 10-ish megahertz, kinds of things with a 6 micron gate length, right? And of course, we obviously are going to push the lower, we're obviously going to push the frequency up on the JFETs by going to smaller gate lengths too.
So there is basically two more short questions. One is, can you comment a bit on the A to D converter and the architecture you opted for the space application?
Yeah, we're using a SAR converter, for what we're doing now. I mean, we've kind of played around with some others. Again, we're trying to get, doing initial stuff. So these are like 8-bit, 12-bit systems at this point in time.
And the last one, perhaps for this round, there is one question by Omar Abdelbari. If the packaging contributes to the rather low operational frequency of the technology. So he says he noticed that the packaging technology was very elaborated, but he basically wanted to know if the packaging has a significant contribution to the potential frequency of operation, or if the bottleneck is actually in the process.
Well, right now, I would say both. I mean, they both harm you. Okay. So in terms of frequency, you obviously want to get to as much monolithic integration as you can to help you in that regard too. So, but yes, packaging parasitics are also a limiting factor and are also need to be dealt with. Yes.
Perfect. Very good. Okay, that's been it. Very much thanks again to Philip Neudeck for this wonderful talk. And we go to the last talk in our today's session, which is going to be given by Agustin Fernandez Leon. Perfect, you're already there.
Yes.
So I can just introduce you with your bio. Agustin actually works as a lead microelectronics engineer at the European Space Agency and in the European Space Research and Technology Center in the Netherlands. He has worked for almost a quarter century, like for 24 years, it says here at ESA. 20 of them as head of the microelectronics section, providing technical support to ESA missions in the area of ASICs, FPGAs, IP cores, design and technology. Before that, Agustin worked for 9 years at Alcatel in Madrid as digital ASIC designer for telecom wireline applications. He has a Master of Science in Electronics by the North Carolina State University and a Bachelor of Science in Physics by the Universidad Complutense de Madrid. It is our pleasure to have Agustin here for the final talk. Agustin, your stage.
Well, thank you. Thank you for the introduction and welcome everyone to the last presentation of this very interesting workshop. So I will be talking about, yes, some very important books that we use as a reference for our development of the space chips and also the IP cores, the building blocks of these chips. What I will be capturing in my talk is 3 major points. First, I will talk about the ECSS standards to develop the end-to-end development of the ASICs, FPGAs, and IP cores for space applications. Then I will elaborate a bit on the special handbook, also belonging to the same system, that compiles a long list of mitigation techniques against the radiation effects of the chips. And I will conclude with a brief snapshot of what are the latest ultra tips on micron activities for the next generation of these space microchips. So the ECSS standards, this stands for European Cooperation Space Standardization, is a family of documents that are specifying requirements that have to be applied every time we have a European space development. And that means that companies that are developing anything from a big space system, a full satellite equipment, so this satellite or specific items of hardware or software for this space mission, have to apply and comply to these ECSS so-called requirements. And that also, of course, includes the development of microchips. Now we also need to be aware that the possibility to modify or even to waive some of these requirements is possible. This is something that is up to the customer and the supplier to negotiate. And in fact, some of these standards already include what we call a pre-tailoring according to, for example, the criticality of the technology or the type of technology that is being used. Now, in this big system organization of documents, we have different branches. And if we look into the space engineering branch, and we observe that we have also several documents there, and the space product assurance branch as well. Now we have 2 main types of ECSS documents. One of them would be what we call the standards, which include normative requirements, things that have to be applied and complied to. But we also have the handbooks, which are books containing guidelines, good practices, and other data that can be used as a reference. Now, in the talk of today, I will focus on the 2 documents that you see now listed there that belong to the electrical and optical engineering discipline. But I will also speak briefly about a complementary document that is sitting inside the Tripoli components discipline of the product assurance branch. So it's 3 documents that I'm referring to. The full titles you can see now on the screen. So the ASIC FPGA and IP core engineering standard, the so-called EST 2040. Then there's this handbook, EHB 2040, that compiles the radiation effects mitigation techniques. And as I said before, there's the ASIC and FPGA IP core product assurance that complements the backbone of these 3, which is the space engineering ASIC FPGA and IP cores engineering standard. So we focus from now on this space engineering standard, which was published last year, and it was replacing what is now the obsolete standard QST6002, which was before published in July 2008. What is the scope? What is this document for? Well, this document is meant to guarantee or ensure the successful end-to-end development of any digital, analog, or mixed signal IP core or ASIC or FPGA. And when we say ASICs, we have to understand this in the more generous way. For example, a microcontroller would be a special type of ASIC. So it would be a microprocessor, even an ADC or DAC component is considered to be an ASIC. So to summarize and not to repeat all of these terms every time we assign the special word device or devices to any of those. Now, these are monolithic devices, but we also acknowledge the fact that this standard can be applied to non-monolithic system in package type of devices, simply by applying the standard for every specific die or chiplet, and then also applying the standard to the final product, assembling the chiplets in a system in package. Now, this is a standard that can be seen as a very good reference for companies who are working with ESA for the first time in developing a chip or an IP, but they also have to be applied by very experienced companies or primes, simply and many times adapting the standard to their own company internal methodologies and standards. What is not in the scope of this standard is to elaborate on the selection process for the existing devices, so the control, the procurement, any type of usage, or even the quality evaluation of existing devices, because this is meant for devices that do not exist yet, that are being developed or will be developed. In the cases that we are doing any of the second item, we have another system of documents that is called ESCC, and I explain what it means here in the last bullet. So let's focus on the main chapters of this standard. And you can already guess, you go to the chapter 5, the device engineering, and you see that you will find general requirements that are applicable to all of the following phases, followed by specific requirements to belong to the so-called definition phase. Then we move on to what we call the architecture definition phase, the design and verification phase, the detailed design phase, the layout phase, implementation phase, validation, qualification, and acceptance phases. We have a special chapter 6 that is containing as I explained before, a pre-tailoring according to device criticality and device types to waive or relax some of the requirements that you will find in these other chapters. Now, very importantly, we also have 12 annexes to this standard that contain the vast majority of the requirements. I mean, they explain in detail what 9 specific documents should contain, but by explaining that, they are also calling what are the requirements to be applied. This would be the list of the annexes. So you will find annexes, for example, describing in detail what the device requirement specification has to include, and likewise for the device development plan, the verification plan, the validation plan, if there is a support and maintenance plan as well. The feasibility and risk assessment report contains a feasibility and risk assessment requirements, the architectural definition report, the data sheet of the device. Also, there's an experience summary report that is requested. And there are a few other annexes listing, for example, variations to the generic flow that are accepted, a list of all the expected outputs in every phase, and then also an equivalence of the phase and milestone terminology with respect to 2 other standards. This standard contains a total of 302 requirements, if I didn't make a mistake, and is addressing digital ASICs, analog ASICs, FPGAs, and IP cores. And you can see in this table that the majority, almost 80% of the requirements, are applicable to all of the 4 types of devices. There are also a few that are all applicable to analog ASICs, or the analog part of a mixed-signal ASIC. And then, as you can see, a few that only belong to 2 or 3 of the 4 different classes. We also have to be aware that not some of the requirements, 12%, are what we call conditional requirements, meaning that they are applied only in specific cases. And there's also 14% of those requirements that will be relaxed or even waived completely if what we are developing is a non-critical or a very low criticality device, which means a device that will not put in jeopardy the entire mission, or that can cause catastrophic consequences if the device fails. So only if minor consequences are expected, we could relax some of the requirements. This is the general flow, the general development flow that contains the 7 phases that I already read when we were reading the first chapters. And in every phase, we conclude with a special formal review where we are checking the expected outputs of each phase. So that means that when we in ESA say that a device has been ECSS qualified, that means that all of these reviews have been passed successfully, because all the expected deliverables or all the expected outputs have been checked, and both the customer together with the supplier are happy with the results. So what I intend to do now is a very quick walkthrough the development flow phases, which in this new expanded picture, you can see that it's busier because I included the expected outputs, the main expected outputs, which in summary account for the device requirement specification at the beginning, and then we have different plans for the verification, for the validation, for the testing that are also produced during the different phases, followed by reports indicating the results of executing the plans. There's a database that is also in the center of the figure that keeps on evolving as we add on elements that have been developed during the chip development. And also sometimes we expect some hardware and some software in these phases. So the first phase is what we call the definition phase. So it is a phase where we are expecting to take from the system definition phase all the requirements at system level and flow down carefully and also in a traceable manner the specific device requirements, so that the team can start developing the device and designing the device. So this is what we would put in the device requirement specification. We also, very importantly, have to define the development plan, including everything about the resources, the tools, the people that will be working on these developments and the timing of it. We will generate the preliminary verification and validation plans. If there's an intention to have a maintenance plan, this is the time to have the preliminary version of it. And then these 2 documents that are circled in green are special documents that will continue to be progressing throughout the entire development phases of the chip, where we assess the feasibility and the risks phase after phase, and we also report on that to the customer. And then the device verification control document will be listing also all of the items that will be subject to verification and the status of the verification of those items. The next 2 phases are what we call the architecture definition phase, where we will be elaborating in more detail on what we call the architecture of the device at block level, all the different blocks, all the different interconnects and interfaces, the inputs and outputs and so forth. And we will be getting things ready to afterwards enter what we call the design and verification phase, where we are already working on the design verification, the actual design entries and design coding, if we're using coding, and the verification of those designs at that level. All of these would be what we can also call and refer to as the pre-netlist level. The verification plan will be also finalized and optimized. The database starts to be assembled together with the first modeling of the blocks of the device. Sometimes we could even see the generation of intermediate or first prototypes of the device to help with the verification of the first definition of the devices. While we continue to work on the feasibility, the verification control documents, if there is a data sheet, we'll also start preliminarily defining that data sheet. The two next phases will imply that we are generating the netlist of the device and reporting on the verification of it. We continue to update the database. Maybe there will be special prototypes also at this level. Feasibility and risk analysis is refreshed, and the data sheet also continues to be updated. The layout phase, after generating the netlist, if it's an ASIC, it will be working on the layout of the ASIC. And if it's an FPGA, we will be doing the place and routes. And the rest of the documents continues to be updated with the special note that the validation plan for the testing of the final hardware device has to be also updated, because then we arrive to the implementation phase where we are either manufacturing our ASIC or programming our FPGA. And in this phase, we expect to review things like the ASIC production test report, or if it was an FPGA, the device, the programming test report to, yes, have some evidence that everything went well in the programming. And with this, we arrive to the final phase, where we should be having the final validated devices, concluding the maintenance and support plan, if there was one. Of course, implementing the device validation, all the testing at system representative level with a good validation report. If there was a radiation test plan, that would be the time to execute the validation, the radiation testing, sorry, and produce the reports. And that will conclude the end-to-end device development with the status of what we call qualified and accepted under the ECSS scheme. Now, what are the radiation hardness requirements, and how do they see deployment in this flow? So first of all, as I said, there will be some radiation environment resilience requirements dictated at system level that will have to be flowed down to the device definition phase and to the device requirements. This is what we would like to have at the end. Device-specific radiation endurance requirements in the device requirement specification. Then in the definition phase and the architectural definition phase, where we continue the definition with lower granularity, we will have to define what are the radiation hardening techniques that are expected to be applied at all the different levels of the developments, meaning, yes, the architectural level, but also farther down, pre-netlist, netlist, layout, and physical implementation as well. We will, in these two first phases, also do an assessment of whether or not those techniques are feasible and what are the risks of applying those hardening techniques. And then we will have to define also how are we verifying those the correct implementation of the hardening techniques. So the verification plan is something that starts at the definition phase and gets finished by the design and verification phase here in blue. Obviously, we will have to implement those radiation hardening techniques, and those are implemented at different levels during different phases: architecture, pre-netlist, netlist level, and even during the layouts, there will be, or there could be, some layout-specific mitigation techniques being applied. We have to apply those techniques, and we have to verify that they were applied properly and report on that with the verification report. And after the device, the final device, has been manufactured or programmed, we have to perhaps conclude with some testing and some validation strategy for the same techniques being in place, for example, with the radiation plans and the radiation test plan. Finally, yes, we have to perform that validation plan and report on it in the last phase. Let's go now diving into the handbook, which is a complementary book, also in the same system as I explained before, that is referenced, of course, from the EST 2040. This is a handbook that was published already in September 2016, quite a few years ago. So it's not perfect, it's not exhaustive, but it's a very good compilation of about 78 different mitigation techniques. This is the result of the work of 13 different companies and institutions during several years. There was a total of 31 experts. I was counting that they were involved in it. We also include a list of different validation techniques to validate that the mitigation techniques were applied correctly. And there's an extensive bibliographic list of references. Now, there are many techniques that can be applied. We heard about many of them throughout the workshop today. And yes, they belong to different stages of the development. They will have to be applied by different people. So what we did at the beginning, when creating this handbook, was to organize a way to present them in an orderly manner. We ended up creating 10 different groups. And also we speak about 4 different major levels at which these techniques can be applied. So the first level is the lowest physical level, the manufacturing process level, where we heard already about different techniques such as implementing guard-band rings, things to be done with epi layers, buried oxides, etc. Then we move upwards at what we decided to call physical layout level. So things like what we heard today about the enclosed transistors, for example, would belong there. We have another group of techniques that we capture into the analog IP items, elements in the chip, within which we find the embedded memories as a special case. And we heard about that too today. An extensive large group of techniques that can be applied for digital design, digital IP in our chip. Then we have also a special group formed by the ASIC standard library cells. And this is painted in pink and green because it really is a blend of digital and analog design. All of those belong to the level that we ended up calling circuit architecture level, because it's a higher level when we start talking about the system on chip mitigation techniques, where we blend and we put together elements of digital, analog, and mixed signal. The FPGA case was also found to be a special case for which we dedicated a chapter in the handbook. And here you can see that all of these in the brackets belong to the so-called radiation hardened by design, as opposed to the bottom one that would be radiation hardened by process. All of those techniques are implemented inside the integrated circuits, but we can also do things outside the chip by playing with the software and mitigating some of the effects with the help of the software, or else also with other chips, other electronics outside the chip in the PCB. That would be what we call the outside integrated circuit bundle of mitigation techniques. That includes also the shielding that we heard about before. And that group is what we call the electronic system level of techniques. And as I said before, we have to be aware that not everyone, not the same person will be implementing these techniques. I mean, we will have PCB designers working on the outside of the chip mitigation, the software designers. We will have ASIC designers, FPGA designers working on the middle ones here, system on chip level. But then we will need to have specific analog designers or memory cell designers if we want to tackle mitigation at those levels. And likewise, if we are working on the ASIC libraries and we are working at transistor level, or the logic cell level, yes, that will probably be done by specific engineers working at those levels. The handbook main structure looks like this, and the main chapters in orange are the main groups that are presenting the different types of techniques, mitigation techniques. There's a 16 chapter dedicated to the validation methods. And it is important to say that this handbook also had a different name in the past. It was superseded also in October last year, and it was called before QHP 6002. Since October last year, it is called EHP 2040 to associate it to the new engineering standard. And it's also important to be aware that this annex, that it's an informative annex that was trying to list vendor and institute ready solutions that include mitigation or help to mitigate, is in a great deal obsolete already and needs urgent updates. And that will be done hopefully next year. Now, the first chapters of the handbook are addressing a description of the radiation environment and integrated circuits. We heard about this on the first talk today a lot. And there's a special chapter 5 that is dedicated to help on the very hard task of choosing a device hardening strategy, the optimal strategy, and also how to use the handbook. Now, in every group, in every chapter or group of mitigation techniques, you will find an overview of those techniques. You will find a summary table of the different mitigation techniques in that group, and also which specific radiation effects address, you know, the SAT, the SAU, the TID primarily. And then you will find sub-chapters where you will see specific mitigation techniques that belong to the same group, describing the concept of those specific techniques with figures. There will be also a reference to real data taken from simulations, radiation testing, or even in flight observations, with the bibliographic references to real cases that was used to verify and validate, those mitigation techniques. There will be a reflection of what are some of the known issues, some of the weaknesses, some of the elements to be considered. And it concludes every time the subchapter with another table that is listing some of the key characteristics of those specific mitigation techniques, meaning what is the abstraction level that they belong to, some of the pros and the cons, which effects are mitigating, and also an indication of what suitable validation methods can be applied when you're using that technique. Now, I have to move very quickly because it's late and it takes a lot of time. I will present you now with one slide per technology group. There you can see, for example, in the first one, dedicated to technology selection and process level mitigation, that's things like using specific epitaxial layers, silicon insulator, triple wells, buried layers, dry thermal oxidation, implantation into oxides are examples of the techniques that are well explained in detail in the handbook. We even have in this chapter a bullet dedicated to a comparison of how technology scaling is affecting the radiation effects, and we hear about that too today. Then we have the layout and analog circuits chapters. And again, we heard today about different type of enclosed layout transistors or ring transistors, but also the contacts and the guard rings, the damming transistors that are used sometimes also to mitigate, and also playing with the sizes of the width and the length of the gates to minimize the effects. This is what we call the layout level or the layout group. For analog circuits, again, we have quite a long list of different techniques that can be applied. And I think we heard about many of them also today from the different speakers: filtering, resistive decoupling, different types of redundancy, differential design, dual path. The group of embedded memories is listing some of the most typical hardening techniques, resistive, capacitive, and then some of the proprietary with the name techniques For example, the IBM hardened memory cells, the HIT cell, the DICE cell, two NASA hardened memory cells examples. But that would be for individual memory cells. We also can play with the bit interleaving when we have memory arrays. And of course, the very famous data scrubbing of the memories to fight back and to mitigate the effects. We have a comparison table of the hardened memory cells. We have a group dedicated to the radiation-hardened ASIC standard cell libraries. And this might not be exhaustive, but at the time, this was a list of the main existing libraries today. So as you can see, we have libraries from IMEC, from CERN, from BAA Systems, from Ramon Chips in Israel, from Geisler, from Microchip, of course. ISA has invested a lot of resources in the libraries from Microchip, but also from ST Microelectronics, Red Cat, who was also one of the presenters. They also own and have their own Rad-Hard libraries. I have one special slide to cite one example, because with IMEC, the so-called design against radiation effects, it's a good example of something where ISA has been working for 2 decades already. And they have now a nice portfolio of different platforms, as they call them, but every platform also includes a library of standard cells. As you can see on the right, they are tailored for different manufacturing processes from UMC, XFAF, TSMC, even Global Foundries, different technology nodes. And in this nice table that they have on their website, you can also observe a summary of which were the mitigation techniques employed to fight the TID effects, the latch-up effects, and the single event upsets for each one of those libraries. So here's the explanation of the guard bands, the deep and wells, buried oxides, enclosed layout transistors, back bias, specific type of Rad-Hard SRAM cells, the dice on the HIT both, BMR, etc. This is one example. And we continue, we move on. In the handbook, we have a chapter dedicated to the digital circuits level. And there we have 2 big groups, the spatial redundancy with different types of TMR. We have temporal redundancy, 2 types of temporal redundancy mitigation techniques. And then we also include a chapter or a subchapter on fail-safe, deadlock-free, finite state machines, explaining how they can be implemented. And also the fact that selecting wisely your logic cells and the clock and reset planes is also helping with the hardening against the effects. We arrive at the top level, the system on chip, where we are combining already a lot of functionalities. And there we included the error correcting codes, different styles, and there are many, as you can see in this list, and probably it's not exhaustive either, from low density parity codes to Reed-Solomon, single error correction, dual error detection, Hamming codes, Boucher-Chaudhry codes, the CRCs. But we also, in this system on chip block, included the mitigation of the memory blocks, the filtering of the SET pulses in data path, watchdog timers, and also TMR in mixed signal design circuits. Like I said, there's also a special chapter dedicated to field programmable gate arrays, FPGAs, and there you will see a long variety of variations of triple modular redundancy, local, global, large grain. Again, this is to some extent arbitrary, the names, but okay, they were cited with examples of real cases where any or some of these types of TMRs were applied. Also applying reliability-oriented place and routes algorithms, specific tools. This one is from Torino in Italy, but also embedded processor protection. Then we have a block dedicated to the partial reconfiguration or scrubbing of the reconfiguration memory. And there, again, you can have the full or partial scrubbing or partial reconfiguration employed to mitigate the effects. And then the 2 off-chip mitigation blocks, one dedicated to the software, where we find things like the redundancy at instruction level or task level if we move upwards on the abstraction level, all the way up to the full application level if we're using a hypervisor, complemented by the system architecture, again, off-chip mitigation, where we use either anything from shielding with aluminum, or another type of watchdog timers at system level. We employ, or we might employ the power cycling and resetting to also rinse out accumulated effects, latching current limiters, followed with the spatial redundancy duplex and triple different styles of using lockstep or double duplex tolerant to transients mitigation techniques. Error correcting codes are also listed here, and also the off-chip SCT filters that can be applied as well. So it's a lot of mitigation techniques, and it's important to be able to validate that they were applied correctly. And this is why in chapter 16, we list fault injection validation methods at transistor level, at gate level, at device level, at system level. There are many ways of doing this. Different tools can help us to do that, and this is what the chapter is trying to summarize. We can, of course, subject our systems on chip to the real life radiation test if we put them inside balloons and some sort of ground level test, where you also employ the real life radiation. And we also can take them to specific ground facilities where we are accelerating the effects with the help of the beams, the radiation beams. So in this area, you will find the methodologies for SE, for TID, a summary of the facilities that we are using at ESA worldwide, and also some other complementary SE test strategies where we might be using laser beams or ion microbeams, or even irradiation of Californian or americium sources to do SE testing. It's a lot of information. It's, like I said, 78 mitigation techniques listed in the handbook. We separated them in 9 different chapters. And what I also did back in 2018, when I presented some of this at another forum, was to provide some examples of how some of those mitigation techniques were used and chosen for specific space microchip developments that were funded by ESA. So this is what you have on the screen now: 5 examples of 5 different microchips, one multi-core microcontroller from Thales, a monocore microprocessor from Atmel, a multi-core system on chip ASIC that was developed by Airbus, a multi-core microprocessor. This is our state-of-the-art at the moment, a quad-core Lyon, also developed by Geissler in Sweden. And yes, one of the European space FPGAs, the so-called large FPGA, that's, you can observe that they were manufactured using different processes from different fabs, but also using different radiation-hardened cell libraries. So it's important to know both, not only the manufacturing process, but also what were the libraries, the raster libraries used. Because as you can see, ST, Atmel, and ICMEC libraries were used. And I won't be explaining the details because there's no time now, although I am including in this deck of slides some details about which were the mitigation techniques used for each one of them. But you can see that, yes, in all cases, we used something between 11 to 14 different mitigation techniques for each one of these microchips. And if we zoom out at the long list of 78, the crosses here on the right-hand side indicate which ones were used for each chip. And this is what you will find in more detail in my backup slides, okay? So what is important to realize and to accept is that, unfortunately, there's no universal recipe. There's no cookbook or flowchart that can guide anyone to decide properly which are the best mitigation techniques cocktail to be used for your ASIC or your FPGA. We have a chapter 5 that will give you some general guidance on that. But yes, it is very difficult because there are many variables influencing these decisions. I mean, starting, of course, from the radiation environment expected. Also to the sensitivity of the technologies that we have chosen to, or we need to use for the ASIC of the FPGA. Of course, the costs of adding that mitigation, because there will be a price to pay in area, in speed, in power, in performance. And it's also relevant to realize that the experience of the people doing this work and also verifying these mitigations is very relevant. Not to mention, of course, the money, the cost, and the timing constraints. So one last reflection is to think that not because adding a lot of mitigation techniques, the results are going to be better. I mean, sometimes having less mitigation is best or is better, because yes, we might increase the sensitivity areas of the parasitic effects in the device if we combine too many of the radiation effects mitigation techniques. Let me conclude with a few slides changing the subject of what is the ESA main activities walking towards the ultra deep submicron for space. And yes, since the 90s, and in collaboration with other space agencies, research institutes, the European Commission as well, and industry, of course, ESA has been helping to define, to fund, to supervise, and to technically support and facilitate access to rad-hard IC technology and rad-hard microchips for space applications. And in doing this, we always have spent time to investigate and resources to investigate, to evaluate, and to validate the radiation effects mitigation cocktails that we will be applying to the libraries, to the IPs, and in general to the UDSM IC platforms that we are now engaging into since recently. So I will quote only 4 main activities. So the first one is one activity that is already closed that we had with IROC in France, in which we were investigating and evaluating the various radiation effects mitigation techniques that could be applied to UDSM technologies. And in this specific case, we focus on the TSMC FinFET 16 nanometers technology. And in the frame of this activity, we perform technology cut simulations to simulate the radiation effects. We also created dedicated test chips and we performed radiation tests. The results indicated that, yes, the FinFET technology had promising results in its use for space. The TID and the latch-up effects seem to be under control. But yes, of course, the radiation hardening of the memories, of the memory elements was necessary. That was followed up by another activity that was kicked off at the beginning of this year in January with IMEC, in which we continue to evaluate this time the TSMC 7 nanometers, also FinFET technology, again performing a simulation of the radiation effects on this technology, having dedicated test chips, and finally irradiating them. So the status is that just last month, we saw the tape out of the first analog test chip, and we will be seeing the digital test chip tape out, so if everything goes well, in beginning of next year. Now, the 2 following UDSM activities will be rolled out in different phases because these are larger activities. They are being funded by our ESA optional program that is called GSTP EEE. And we have one that it's already kicked off the first phase of it, and it's with Frontgrade Geisler in Sweden. All in all, we have reserved 19 millions to be spent on several phases, but the first phase was kicked off in November, just last month, for 7 millions. And again, this one is focusing on TSMC 7 nanometers FinFET technology. We will be working on different building blocks for the next generation of the general purpose microprocessor for space application on this technology, but also we will be helping to consolidate existing platforms on 28 nanometers from ST in France and from Global Foundries in Germany for the 22 nanometers, and develop some other IP cores that are heavily used in space, those technologies. And the second and last one from this last new bundle of UDSM big projects, it's also 20 millions that we are being reserved. This one is focusing more on interfaces and system in package technologies, and also having as a ultimate target, having building blocks for the next generation European space FPGA, and also, yes, the chiplets paradigm and the chiplets system in package technology. So the status, we are still a bit more delayed with respect to this one. We have the first invitation to tender still under preparation. We still are in the process of confirming support from different companies in Europe. I think it's late. I have 2 more slides providing some more details on the UDSM1 and the UDSM2. I leave this to you to check after I finish my presentation. Like I said, I have plenty more information in backup slides, and I'm including also some links where you can find the standards, the handbook, the website of the ESA Microelectronics, referring to additional documents that can help to apply the standards. Also the full handbook presentation that I gave in 2018. And also 2 events that will be happening next year, where you will find a lot of information on rad-hard ASIC and FPGA developments for space. And with this, I conclude. I will take some questions if there are some.
Thank you very much, Augustine, for the very nice talk. I actually got 4 questions in the chat. So the very first one, which was raised, concerns slide 10, where it says, the question is, in slide 10, is the risk assessment report to be generated in all phases?
Yes, because the idea is that with every phase, we might be introducing new models, new granularity on the level of the models. And also some things might be decided or changed with respect to the previous phases that might have an impact on whether it is feasible or not, or whether it is introducing new risks or not, or maybe we have mitigated risk that were identified before. So this is why we're expecting an update of these assessments of the risk and the feasibility. And if there's nothing new to be declared to the customer, this is the place where these new risks or risk being eliminated should be reported.
Okay, good. The second one which was raised is how do we differentiate the failure in I/O blocks with the failure in core blocks?
Well, okay. Every failure can happen in different places of your chip, of your design, at different. And what you need to do is that every mitigation technique that you are applying at each level comes along with a verification strategy. So if you want to verify that there are no failures at the outputs, for example, yes, you have to cater with specific simulations, or maybe sometimes analysis of the modeling that you did at different levels, focusing on the IOs. But yes, failures can happen inside, can propagate, can dissipate by themselves, and how failures propagate or not is something that you have to prevent from happening with your mitigation, and then with your verification methods, you will have to verify that before you implement the chip or the IP, and sometimes you will need to validate at testing level with your final hardware that indeed your technique is working correctly. That might be expensive and not always doable, but in some cases that would be the only way to measure that.
Good. Then on slide 32, you mentioned these libraries which were developed together with IMEC. One of our participants asked if these libraries are open source.
No, they're not open source. IMEC is the one providing access to them, but they should be available to anyone requesting them to IMEC under the terms and conditions that IMEC has set up. But yes, of course, much of these libraries has been developed with European taxpayers' money, and of course, ESA and IMEC have always work on this with the intention to make them available to the European ESA member states as a bare minimum. And yes, they should become available relatively easily if you are requesting this from an ESA member state.
Okay, good. A last one, which also basically goes a little bit into what we have heard before with non-standard cell libraries for radiation-hardened designs. So Christos is asking, is it possible that someone achieves any radiation hardness using a standard cell library, meaning a non-specialized one, and performing a resynthesis during the place and route phase of the digital IC design? So basically using a standard cell library, but during place and route, taking in some measures for radiation hardening, or do you need to start from scratch in non-standard cell libraries?
Everything can happen. I mean, of course, if you choose to use a standard non-rad-hard library, you better compensate by mitigating at other levels. And yes, it's like the same way we use commercial processes and we make rad-hard chips with them by compensating the fact that there's nothing done at process level, that we do put on top of those levels mitigation at the IP design, at the standard cell library. So no, if you choose to, or you only have the choice of using a standard cell library, you will have to compensate with anything that comes above that. Meaning, yes, the layout is one of the opportunities where you can do something. Also, the topology, the architecture of your design. I mean, plus, as I said, you can even go all the way outside the chip to mitigate. I mean, with software, if there's a microprocessor inside, with the shielding. So yes, anything can happen above levels where you haven't mitigated.
All right, great. So thank you very much again for this answer, and also for the nice presentation, Augustine. And then I think everyone attending so far, we have been losing some attendees in the meantime because we have been stretching our time a little bit, but it's still great participation. So thanks a lot, everyone, for presenting. Thanks a lot for all attendees. And Danielle, do you want to have any final words, or can we close the session?
Close. This is just a reminder that the webinar recording and slides can be found on the SSCS Resource Center. The link is in the chat. And we will send out a reminder when it's posted in the SSCS newsletter or via emails. I'm not sure which one, but it will get sent out. Thank you, everybody.
Perfect.
Thank you, Moritz. Thank you, speakers.
And thanks, Danielle, for organizing it. Thanks a lot, everyone. Have a good night.
Thank you.
Good day.
Thank you very
Bye-bye.
much.
Take
Bye-bye.
care, everybody.
Thank you.
Bye.
Thank you. Bye.
Goodbye, hello.